Okay, so I want to welcome all of you to a new area of extension in DE analysis known as multidirectional efficiency analysis. We are going to go straight to the point to ask the question, what is the multidirectional efficiency analysis? Okay. So multidirectional efficiency analysis, I'm giving you the difficult part first. It's sometimes called the potential improvement method or potential improvement analysis. And why is this so? Because it improves the traditional radial DEA models. How does it improve it? The traditional radial DEA model measures efficiency of a company or a firm, a DMU, by looking at the firm and not the variables that actually were minimized or maximized to arrive at that efficiency score. In other words, the radial DEA model assesses efficiency of a firm or of a DMU. It does not assess the efficiency of the variable. Now, technically, it assesses the efficiency of the variable, but because of the radial nature, the radial nature says that there is proportionality. The same ratio is given, okay? So the same proportion, so if you increase the inputs by 20%, the output increase by, a certain amount. But the key point is that the rate of increase of the input is the same. So if you are increasing one input by 30%, all the inputs are being increased by the same 30% because of the radial nature, because of the proportionality assumption. So even though you can calculate the efficiency of each variable in the normal DEA, the variable's efficiency is going to be the same. The efficiency of the variable for variable x1 will be the same efficiency score for variable x2, and that will be the efficiency score for variable x3. And so eventually, that will be the efficiency score for the DMU because it started there. Now, this part that I'm saying is very important. But the MEA, or the multidirectional efficiency, you come to understand why it is multidirectional. It looks at efficiency of the variable the same way that ordinarily the DA would have done, but because the direction, that's why the direction efficiency comes. The direction in which each variable is being measured is separate. They are all not being measured in a radial direction. They are being measured in a non-radial direction, and therefore it makes each variable, whether it's input or output, have a different direction. Direction towards where? You can tell me. Direction towards where? Albert Bensusa.
Towards the frontier.
Towards the frontier. How we all arrive at the frontier is important. Okay. So if you have a frontier like this, and then you have a particular unit here. Now, obviously, there's going to be Y1 and Y2 for this. Okay, and this guy is here. Now, this guy can get to the frontier in this format, or can get to the frontier in that format, in this format, in that format, or can get to the frontier in that format, or in that format, or in that format. So we can still get to the frontier, but if I don't want this portion of the frontier, depending on the method, if I don't want to arrive at the horizontal and the vertical section of the frontier here, I will not use this measure. Okay, I will not use this measure. I will use a different measure because I want to arrive at a strongly efficient part of the frontier. And please take note, the strongly efficient part of the frontier is different from the weakly efficient part of the frontier. So if I have a point here A, and then a point here B, and a point here C, and a point here D, where is a strongly efficient part of the frontier? Chris, where is a strongly efficient part of the frontier?
It's the space inside from the origin to the frontier. So that would be the area where A is.
Okay. Now, that is not correct. Godwell, where is a strongly efficient part of the frontier?
It's between the line B and C.
That is it. That is a strongly efficient part of the frontier. First of all, it has to be the frontier. So the strongly. Now, where is a weakly efficient part of the frontier? Albert Kofi. Where is a weakly efficient part of the frontier?
So it's A and D. Between A and D.
Okay. And what else? Between A and B.
And then Y1 and then
This one is DO. This one, yeah. Okay, so I've added F. Emily, what is it? What do you think he's trying to say?
Okay, so Doc, the weakly efficient parts will be between A and B, and then C and D.
Okay, so God will take. I'll be taking note of that. Now I've stretched the frontier between B and C, and I've created an extended point, which is F. Now, between B and F, let me stretch it further. Dear me. Anyway, you can't get my question. So let me rather do this. So the most strongly efficient part of the frontier is where? And be careful.
Okay, so Doc,
now you have A, B, G, F, C, and D.
Yeah. Okay, so with the new graph, the strongly efficient one becomes the G and F.
Not the strongly, the most strongly efficient.
Okay, so the most strongly efficient will be between G and F.
Why?
DMUs that are found between G and Doc, because they have how do you put it? The between B and G is now part of the straight line, which is the free disposable line. So
it's not a straight line, no. It's a curved line. I just want you to know that it's still a curved line.
Wow.
It's not straight. I've drawn the thing badly, but let me just clarify it. Suppose you have this, okay, you have that, then this, then this, then that, then this. Okay, so now you have A, you have B, you have C, you have D, you have E, you have F. Now, where is the most strongly efficient part of the frontier? This is important. Don't be confused, but be confused. Godwell. Emily. Come on, go.
Between C and D.
It is between C and D. Now, why is the B and C and the D and E not the most strongly efficient part of the frontier? Why are they not? Well, the answer is that they are closer to the free disposable section. You see, this part here is closer to the free disposable section. So let me tell you, if a guy is here, this is important. This is a non-radial part here. If the guy is here, okay, let me put it this way. Let me put it even this way. If the guy, I'm strategically positioning this X variable. And this guy has a choice to go here to become efficient and has a choice to go here to become efficient. Which one should he go for?
Doc C,
Why?
because C is farther away from the free disposable line, so it will make it more efficient to be at C.
That is why C is the most strongly efficient part of the frontier. This is important. So it's not just those that are on the horizontal lines or the vertical lines that are said to be, inefficient in a weak sense. If I have a choice to go to B or C, I'll choose C because C is towards the most strongly efficient part of the frontier than B. This is very crucial. So keep that in mind as we delve into this. So the variable specific efficiency is also called the patterns of efficiency. Take note. Okay. The patterns of efficiency is different from the status of efficiency. The status of efficiency is the overall efficiency of the firm. Write it down. Is the overall efficiency of the firm. Whereas the patterns is the variable specific efficiency of the firm. Chris, did you get what I said?
Yes, Prof.
Explain.
Please do again.
And Chris will explain again.
You said the status efficiency reflects the overall efficiency of the firm, whilst the variable specific talks about the efficiency of the DMU.
No. That's not what I said. Albert Ben Susan, explain. Unless you should have asked me the question that I don't understand, like Godwell is asking. But because you didn't ask me, I'm asking you.
Okay. So you said the status efficiency is the overall efficiency of the firm, while the pattern efficiency is the variable specific efficiency. Variable specific efficiency.
Good. So if there are 4 variables and 1 DMU, how many patterns of efficiency and how many status efficiency do we have? Albert Kofi. How many patterns of efficiency, how many efficiency patterns do we have? And how many status efficiency do we have? Albert, are you here?
It will be 4. Part 4 percent of efficiency. Yes, I'm here, Doc. Doc, I'm here.
Go again.
Hello, Doc, I'm here. Hello, Doc, I'm here.
Yeah,
I'm
go
saying that
ahead.
it will be 4 patterns of efficiency. Doc, it will be 4 patterns of efficiency.
And then how many status efficiency? How many efficiency status? How many efficiency patterns? Emily.
Doc, it will be 4 patterns and then 1 status.
Okay. Very important. Document this. You see, this is where you learn and you learn one time. This is not where you learn and you say, okay, I'll go for the recording again. You're wasting time. This is where your knowledge concentration must be. All right. And you can use that same principle to calculate productivity. Okay, we'll come to that next week. All right, who introduced the MEA? It was originally introduced by Bogedorf and Hugard in general productivity analysis, then operationalized by Asmald et al. In 2003. Then in 2004, Bogedorf and Hugard actually brought the properties the characteristics of the MEA clear. So note the people behind. It's very important. And note the year. It was propounded, but it was that much ignored, until recently. Okay, so is it a non-radial model? Of course it is a non-radial model. What do we mean by non-radial models? They are models that don't move in the proportionality of the inputs and outputs. When you are estimating non-radial models, they are not in proportion. Now, what do we mean? For the newcomers, what we mean is this. If you are estimating an input-oriented efficiency score, and the efficiency is something like this, and all the firms are inside, so let's say that you have firm X here. If you are trying to estimate the efficiency of firm X, the way you got to do it is you take it from the firm towards the origin. That is how you estimate it. In the process, the distance from the axis here to the line, and the distance from this to the line, the ratio is maintained as you go further. Okay, as you go further, the ratio is maintained. As you go further, the ratio is maintained. And because you are maintaining the ratio, so if you are increasing the horizontal axis by 20%, and you are increasing the vertical axis by 10%, it's going to be 20%, 10%, 20%, 10%, 20%, 10%, all through. You are not changing it. You are not changing it. Are you with me? So that is what we mean by radial. Radial is also called proportional. So that's what we mean by radial. To get to the frontier, okay? So this guy will go in the direction of the frontier. So if this X guy wants to be reduced, the movement it would have to take is this way towards the what? The frontier. But then the non-radial guy will not go here. He will go this way, not in the direction of the origin. No, not like this. But in this direction, non-radial can go in that direction. Non-radial can go in this direction. Non-radial can even go in that direction. Non-radial can go in this direction. Non-radial is going outside the direction of the origin. That is non-radial. And in the process of that, non-radial methods, most of them are able to consider input excesses. Input excesses, that is too many of the inputs that are being used, they're able to identify that. And too many of the outputs that are too smaller of the output, too short, too little of the outputs that are being produced is able to identify them. And these are known as slacks. So non-radial models then capture slacks. Okay. Such non-radial models are able to optimize a measure that aggregates input excesses and output shortfall between the benchmark and the DMU under evaluation. Now, non-radial models can be oriented, non-oriented. They can be oriented and they can be non-oriented. Now, what do we mean? And again, that goes to you, Emily. Because if I should ask you, what is the difference between oriented measures and non-oriented measures? What is the difference?
Okay, so oriented measures usually means that we are looking in one direction. So if it's input, we are considering input orientation, or if it's output, we are considering output orientation. But when we say non-oriented, that means we are looking at both the input and output at the same time.
Direction where? You say one direction. Direction where?
Yeah.
Direction towards where?
It's towards the frontier.
It is important that you always add that. It's in direction of the frontier. Okay. Towards the frontier. If I am inside, like I just showed you, I am moving downward in the direction towards the frontier. If the frontier is rather above me, I am moving upward in the direction towards the frontier. But in these directions, the non-oriented directions is multiple, you're affecting both the inputs and outputs at the same time. Okay. Guys, if you don't understand, you ask. So it's not when we've gotten there, then you start asking. All of these measures you see on the screen are non-oriented. They are all non-radial models. They are all non-radial models. Now, some of the non-radial models can be oriented. Well, all of the non-radial models are oriented and non-oriented. Take note. But not all of them are, no, all of them are oriented. All of the non-radial models are oriented, but not all are non-oriented. Take note. Not all of them can be used to simultaneously cut input and raise output. Not all of them can be used to simultaneously cut input or raise output. These are the points you note down.
Doc, please, can you repeat that?
The non-radial models, okay, not all of them are non-oriented. They are non-radial. They are all oriented. In other words, they can all use input orientation and output orientation separately. But not all of them can do input and output orientation simultaneously. For example, the directional distance function can do both oriented and non-oriented. But then the additive model cannot. You have to do one at a time. So some of them you have to do one at a time. Others, you can do one at a time and you can do all at a time. The key one we are going to look at is the one at the bottom. That is the one we started with. Okay. Now, that does not mean that the radial models are not good. They are good. We've seen this already before. They are unity invariant. Okay. They are unity invariant, but their disadvantage is that they ignore the slacks. So how does the MEA work, really speaking? I've given you a lot of references here to check the power of this MEA. How does it work? Watch this. MEA selects benchmarks. What are the benchmarks? I'm going to call the new ones. King, are you here? Are you here listening, or you've just joined?
Yes, Doc, I'm here.
Okay, in your reading, what have you learned? What is the benchmark? If you don't know, pass it to Abdul and let's go. King, are you here?
Yes, Doc, I'm here.
I say if you don't know, you should do what?
Abdul. Yes.
You should do what I say, Abdul.
I should pass it to Abdul.
So call him and tell him that you're passing so that he is aware. But if you just keep quiet.
Yes, Doc.
Doc,
Abdul, I'm
please,
passing
I'm now trying to grasp.
So you to pass it to somebody. Abraham.
Christopher.
You're passing it to Christopher. Okay, Christopher, go ahead. Chris, are you here?
Am I the one?
Yes, you're the one.
It's the most efficient DMU pair that we can compare to the inefficient ones.
The most efficient DMU that we can compare to the inefficient one. Albert, what would you say are the benchmarks?
Yeah, so I'll say that they are the DMUs the most efficient DMU.
Emily, what are the benchmarks?
That I'll say is the target DMU that shows the inefficient DMUs what they can do to improve.
The benchmarks are not necessarily DMUs. Yes, Ken.
Doc, he said, I was coming to say they are the DMUs on the front here.
Yeah, not
okay, so Doc, they can both be real and virtual. Hello, Doc. Please, you're muted if you are talking. Hello?
Just a second.
Okay.
All right. Sorry about that. So the point that Emily you said is critical. Guys, the benchmark can be a DMU and it can also not be a DMU. A benchmark is not necessarily a DMU. So when you have a graph like this, okay, and then you have that, and then you're trying to create a frontier like this. You have one there, you have one here, you have one here, and then finally you have this. Now, if you have a particular DMU inside this whole analysis, so if you pick a DMU like this, a DMU like that, okay, and you are trying to estimate the efficiency of this particular DMU, if you trace this, okay, and then it goes to hit this portion of the frontier, that is a real DMU. But if you trace this and it hits that portion of the frontier, that is a benchmark. That is not a real DMU. The real DMU is not there. The real DMU is here. This is where the real DMU is here. Okay, it's at the junction. These are real DMUs. These are real DMUs. Okay, but they can also be what? Benchmarks. So real DMUs, or what we call peers, real DMUs are benchmarks. All real DMUs, all peers are benchmarks, but not all benchmarks are peers, because here at this junction here, this guy is a benchmark. Okay, this guy here is a benchmark, but he is not, or it is not a real DMU because it is a linear combination of real DMUs. If you hit another portion here, it is not a real DMU because it's a linear combination of peers or real DMUs. It is, so this is called target or benchmark. I think it's clear. If it's not clear, say it. Is it clear?
Yes, Doc.
Yes, Doc, it is.
Yes, Doc.
I'll ask you again. So that's why it's going to come up many times today. Okay, so it's important that you understand. Okay, so when you read all of these papers, they'll tell you. So what MEA is doing is that it's selecting benchmarks. It's not selecting real DMUs. It's not selecting peers. It's benchmarks. And these benchmarks, once it selects them, it does an input contraction. So it reduces the input or increases the output proportional to the potential improvement. This word is very important. Proportional to the potential efficiency improvement. Proportional to the potential efficiency improvement. Now, what do we mean by potential efficiency improvement? Emily, what do we mean by you're in trouble? What do you mean by potential efficiency improvement?
Okay, so
is it the efficiency score?
Yes, that's the thing you mentioned that the theta, when we are doing for normal DE, when we are doing input orientation, we maximize the theta to get the actual, that's the theta star. So we call that the potential improvement, efficiency improvement.
So guys, write this down. This is very important. The potential, remember what the MEA is doing is that it's selecting a benchmark and it's selecting the benchmark in such a way that you are reducing the input to increasing the output But these input and output improvement, they are proportional to the potential efficiency improvement. That is identified by considering the improvement potential in each variable separately. So what is a potential improvement, efficiency improvement? It is not the current efficiency score. Note it down. It's not a current efficiency score. It is not the amount of slack. It is not the overall inefficiency of the DMU. No. It's very, very important. Did you identify what it is not, Kane? Did you identify
Yes,
what it
Doc.
is not?
He
It is
said
not what?
it is not the current efficiency score. It is not the amount of slack, and it's also not the overall inefficiency of the DMU.
Very important. It's going to come back again and then you get confused. So that's why I told you to write it down. It is more practical. It's more practical and a managerial, the potential efficiency improvement. So pay attention what it is. The potential efficiency is asking this managerial question that if this particular variable were managed efficiently as the best performing DMUs, if it was managed efficiently as the best performing firms, how much could it realistically improve? That's what the potential efficiency improvement is asking. How much could it realistically improve? How much could it realistically cut down the input? And how much could it realistically increase the output? So it is by how much the inputs are reduced or by how much the output are increased. That is a potential efficiency improvement. So it's not efficiency score of the firm. It's not the inefficiency score of the firm, and it's also not the amount of slacks. Now listen, it is the maximum feasible improvement. Now the word maximum doesn't mean that you are going to increase the input. I didn't say maximum decrease. Neither did I say maximum increase. And you know you can have maximum decrease, maximum decrease. Do you know that? Do you guys know that?
Yes.
Yes, Doc.
You normally use maximum decrease for what? In our parlance. Maximum decrease for what?
Doc, the input.
Yeah, maximum decrease for the input or for what? Apart from the input.
Bad output.
Bad output. Note it down, those who don't know. Okay, maximum decrease for input or bad output. And then you have maximum increase for that. But instead of saying increase or decrease, you say maximum improvement. Because the improvement can be improving cost, which means you are reducing cost, or improving revenue, which means you are increasing revenue. So the potential improvement is a maximum improvement for each input or output given the frontier. That is a maximum, that's a potential efficiency improvement. So it's not what is the actual, neither is it what is the end. It's not what is in the beginning or what is in the end, but it is what is in between. What you do to the beginning to get to the end, that is a potential improvement. Very important. Very important. So that is what MEA is looking for. It's looking for benchmarks that will get us there. So the MEA is more suitable. This is why we say it's more suitable for investigating the efficiency patterns. And in this case, what do we mean by the efficiency patterns? Kane, what do you mean by the efficiency patterns? King,
Doc.
you see, when you don't know, you don't talk, isn't it? You keep quiet. You don't even show that you are present. But when you know, blah, blah. Yes, Chris.
They are the inefficiencies attributable to specific variables.
No. What is efficiency patterns? I didn't say what is inefficiency patterns. I said, what is efficiency patterns? What is
They are
efficiency
variable
patterns?
specific inefficiencies.
Yeah, what?
Variable specific inefficiencies.
Why are you using inefficiency when I've used the word efficiency?
Or efficiency. Yeah, I mean, it's efficiency or inefficiency.
Don't say efficiency or inefficiency. I have asked you what is efficiency patterns. You're changing the word.
Okay, so they are variable specific efficiencies.
Good. Of the DMU. So the
Of a
variable
DMU.
specific efficiencies of the DMU. So a particular DMU can have 6 variables, and then each of the efficiency from these 6 variables. Albert, Kofi, are you listening? Each of the efficiencies
Yes, Doc.
of these variables are what becomes the variable specific efficiencies. Okay. So all of these references will give you a guide. Now, this is not the first time variable specific efficiency measures have been introduced in the literature. It's been there. It's been touched on via something called subvector efficiency. This subvector efficiency was introduced by Fair et al. In 94. Okay. DHC also spoke about a subvector efficiency. I have some notes on subvector efficiency. It's also been introduced in the Russell measures. The slack-based measure of tone. Also, even though we didn't go detail about it, guys, and Emily, that's what you should dig into. You can also look at the variable specific efficiency using the slack base. Because how do you get a variable specific efficiencies? Really, is a target divided by the actual, isn't it?
Yes,
Write it
Doc.
down. That goes to all of you. Write it down, all of you. The variable specific efficiency is the target divided by the actual. That is why I told you that the DEA even calculates variable specific efficiency. The only thing is that it's the same for every variable. Guys, do you remember that the definition of efficiency is a distance to the frontier? That word is the same as the target. The distance to the frontier is the target. Then it is divided by the distance to the firm. That is the actual. Write it down. Write it down. Write it down. You forget. So that same definition carries everywhere. So the slack, if I can use the slack we looked at the last time, if you can get the target for the DMU and you can get the actual for the DMU, then you can get the target for the variable and you can get the actual for the variable. And so you can also find variable specific efficiency under MEA. It's not been done much. Look for the paper by Fuji, Fujii, Fuji et al. Forgotten the exact date, but then the paper was looking at banks and undesirable output in Japan. You should learn this. Why you should learn this is because once you understand this, you'll be able to do yours. So coming back to you, Albert and Chris, if it happens that you are even struggling some way, somehow, to do the MEA one, then you can stretch the DA one. Sorry, the one by SBM. The one that we're just talking about here. You can now stretch that one and then do that very one. Okay. So the paper is Indian. Oh, is it? Yeah, I think it's rather Indian. Indian bank efficiency and productivity with undesirable output, a disaggregated approach. A disaggregated approach. What I'm doing is that I'm just dropping that into your page, and then you can give it to the others here. Or let me even make it easier. Let me make it easier by dropping it into the chat here. How do I drop it into the chat? Let me see if I can drop it into the chat. Yeah, I can. When it shows in the chat here, let me know. Okay.
Okay, that it shows.
So, and that is a directional distance SBM that can also do the same thing. Of course, it's a sister of the SBM. Okay. It's based on your questions that I'm able to give you more. If you don't have questions, I'm not able to give you more. So what are the advantages of the MEA? Well, first of all, it's selecting benchmarks. Okay. And these benchmarks, okay, is doing it, they are not proportional. They are non-proportional to the actual production. But even though they are non-proportional to the actual production, they are proportional to the potential improvement. They are proportional to the potential improvement related to the input or the output dimensions separately. So each one. And we'll show that graphically very soon. The other advantage is that it ensures the characteristics of technological monotonicity. This word was introduced by Bogotov and Hugard, and it was one of the interesting things that they spoke about, technological monotonicity. Now, what is that? What do they mean by technological monotonicity? Well, first of all, it looks like I've jumped some. Okay. I hope you see the slide because the thing is, you see the slide?
Yeah, but
Yes,
some
Doc.
sections are covered, at least for me.
How about now?
Still, the top right side and then the top bottom.
Top right. That is
I
on
mean, okay,
okay.
yeah, you
How about
moved
now?
something. Yeah, you moved it to the middle.
Do you
Okay,
see
it's gone
something in
now.
the middle?
Yeah, that's gone. Okay.
So everything is fine now.
Now there's a bar in the middle.
Hold on. Tell me if there's still a bar in the middle.
No, please, it's gone now.
All right.
Thank you.
So, what are we talking about? Technological monotonicity. Well, as the name sounds, I've given it an implication. Technological monotonicity means that you are improving the performance, and when you're improving the performance, it should never make the DMU appear worse. At least it should make the DMU appear what it was. And one thing is that because MEA is non-directional, it's not radial, it's horizontal, and you're going to see. Because of that, you are able to maintain the fact that the least the guy can do is the guy will not be inefficient, or the guy will remain. It's not going to make the person worse. Now, whilst DA also ensures that the radial nature of the unit can cause sometimes, depending on where it's going, because if it goes towards the free disposable section, and radial can take you there. Let me explain to you what I mean by radial can take you there. Okay. So when you take this one here, this is radial. Okay. Radial can take you, you have this one. And I'm using output all the time because I'll be using input in the real example. If I do radial movement can hit the vertical section here, or it can hit the horizontal section there. And when it does that, okay, that is not technological monotonicity. Okay, Because what is done is that even though you have moved this guy to the frontier, there is that portion here that he should have moved to because there's a DMU here that is dominating it. Okay, there is a DMU here that is dominating this very DMU. And as a result, because this DMU is dominating it, it doesn't make where it is good. But then what the MEA would have done is that it will move it straight away. It will never hit any of this section here. So MEA will move it straight to these sections. Okay. And therefore, that is why we say that it ensures that technological monotonicity. All right. Then another advantage is that it's good for non-orientation. I told you that most of the non-radial models are good for non-orientation. And also if they are bad output, most of you are doing bad output in banking, bad output in energy, like pollution, like non-performing loans. This is where MEA is good, but also SBM is also good for that. But compared to the DEA, this MEA selects the strongly efficient benchmark. You see that word? Not the weakly efficient benchmark. MEA has a stronger translation invariance properties. We know this already. You should read about it if you don't understand it. But if you don't understand the strongly efficient benchmark and the weakly efficient benchmark, you can raise your hand. But MEA is good. It will give you the strong guy. Because the strong guy or the strong target is what you need, not a weak target. The other advantage is that it does not impose the symmetry needed of the radial optimization. That symmetry, which basically ignores the shape of the frontier outside the array from the origin to the point and analysis. Again, this one, the only way you can understand is when we come to the graph, and I'll show you that when we come to the graph. Another advantage is that it separates benchmark selection from inefficiency measures. This is so real and so true. It separates it. Okay. For example, I'm not interested in the inefficiency. I'm interested in the target, and it does that. It can be used in both CRS and VRS. These ones are common. It doesn't vary with respect to the affine transformation in VRS. It remains unchanged. It's just like the technological monotonicity. And then it can include that discretional and non-discretional variables at the same time. What are discretional and what are non-discretional variables? Albert, Ben Susan, what are discretional and non-discretional variables?
Doc, I can't remember.
Okay, Albert Kofi, what are discretional and non-discretional variables?
Doc, so the discretional variables are those that, so let me use, for want of a better word, they are at your discretion. And the other ones are like, you cannot do anything about them. They are strict. They're non-discretional variables.
You know, the best way to explain something is to do what? Anybody can mention it to him.
Doc, give an example.
Okay, go ahead, Masa. That's when I know that you are not lying. That's when I know that you know what you're saying. But those, for the want of a better word and all of this grammar, that you are saying there. Yes, King.
So, Doc, for discretionary, you could say that the managers have control or power over them, but with the non-discretionary, they don't have power or control. So, for our work, for instance, fixed deposit and deposit is non-discretionary because managers cannot control the amount of deposit customers bring to the firm, and employee expenses is discretionary because managers can control how much they spend on personal expenses.
I love this. Is it ChatGPT who is talking or you are talking?
Doc, please, I'm talking.
Oh, I love this. Wow, that is excellent. If it's coming from your coconut, that is really good. Yeah, you are really learning. When I told you, go and watch and learn, you are really learning. That's good. So, guys, exactly as he said, okay, non-discretionary, you can't control them. They are not really under your control. Okay, you can use, but you can't really control. They are not really under your control. And when some things are not, I love the example he gave, deposit mobilization. You can go and collect deposit, but whether the people bring deposit, and you can't. So non-discretionary and discretionary. Also note that there are some that are said to be fixed, and that's different from non-discretionary or discretionary. Okay. So that you can include it here. But here's the disadvantage. NEA, you're going to see, it's not easy. It's not a straightforward calculation. No. It is intensive. It's computationally intensive. And that is why a majority of people don't like to use it, even though it's got all these beautiful attributes. It's complex. You're going to look at two-stage process. That two-stage process is complex because you got to calculate it for each variable. Emily can tell you. You write the codes and you'll be tired. Emily, were you able to ever learn from Eric how to, loop the code and then, extend it, automate it?
Not yet. That one, he was doing it in Python.
It's never good. He too was not teaching you much. The other disadvantage is that it does not lead to the comprehensive efficiency measures. Now, you know that this one is looking at the variable specific efficiencies. When you finish, you should aggregate it. You should aggregate it. And until ASMAD actually introduced the 2012 paper in EJO, where it's possible to integrate it and create a singular efficiency score for the DMU. Because once you have it for each variable, you got to find a way to aggregate them. And that aggregation was a challenge until, they suggested the use of the slug-based approach. But other than that, to have a comprehensive efficiency measure for the firm, you can get it for the variables, but for the firm, it's tough until recently. And the reason why it was tough is because the chosen benchmark may exhibit non-directional slacks. And if it has non-directional slacks, you have to capture that. But here, this one, using the SBM approach, you see that very soon. We are able to capture all of that. So when you use the MEA, well, when you want to identify separate effect, separate contribution of each variable. So let's say that you want to know the contribution of the labor employees towards the overall performance of a bank. But at the same time, you also want to know the contribution of the deposit. And you also want to know the contribution of capital. Do you want to know the contribution of fixed asset? You want to know the contribution of loans and advances, which is known as earning asset. And you want to know the contribution of investments, which is known as other earning assets. If you want to know the variables contributions, respectively, you use the MEA. That's it. What about it? When you also expect that some of the variables have got more capacity to improve than others. For example, do you think that they all have equal capacity to improve? When you believe that some variables are not just there, they are key. For example, you need that CEO. You need the board of directors. You can't joke with it. If you believe that some variables are necessary, you use MEA. When the firm wants to disaggregate efficiency into variable types, it's just like the first one. Then you use the MEA. But I've also told you that the SBM can do that. And then when you want to use both orientations, when you want to include bad outputs and all of that, DEA cannot do effectively, MEA will do. Okay, so let's get into the details. How do you calculate it? Step 1. Emily, walk us through the first step.
Okay, so it reads that You should identify the input or output correspondence of an ideal reference point, that's the IRP, and you do so by solving the linear programming problem for each input and each output separately. So the RLP depicts the largest possible input or output reduction, and then output expansion. That's it. It minimizes each input separately, keeping the remaining inputs constant or fixed. Okay, so Doc, I think basically for the step one, what is that? What it does is, if you pick any of the inputs, you draw the line to take it as far as possible. So the maximum inputs that can be used. I'm trying to picture the graph.
And when you
So
say
for inputs,
when you say draw the line, be clear about what line. Which
Okay.
direction of the line are you drawing the line?
Okay, Doc. So when you pick an input,
Guys, ask her questions too. Yeah, go ahead.
so for the ideal reference point, what it does is for each input, you are able to.
By the way, why is it called ideal reference point?
That because it is the ideal point that you would prefer. So for inputs, that's the minimum input that you can use for the firm, which is usually not realistic. That's why we have the second step to make it realistic. So for the first step, what you are doing is you are reducing the input, if it's output, you are maximizing the output to an ideal point that you would have wanted, the best possible point that you can get. Guys, any question? If I'm not explaining it well.
Guys, Albert Kofi.
Yeah, please come again.
Wow.
Okay, so if you read the last line, it's saying that you minimize each input separately, keeping the remaining inputs constant. So let's say you have x1, x2, x3. So when you get to x1, you're going to, the calculation, it allows you to minimize the x1 to its lowest point possible. And that's what we are calling the ideal point. That's the ideal reference point. So the step one allows you to minimize it to that point. And then the step two will allow you to make it realistic by bringing it forward or adding more inputs if that's what needs to be done for that particular point to be efficient. So you do this individually. So for each input, the step one allows you to minimize it to its lowest point.
Okay, so if I understand, you're assuming that I'm using, let's say, labor and milk, and then I'm currently using 10. Step one essentially says I want to minimize it. My best possible minimum is 5, so I do that to 5, but I don't factor in the milk usage at all, and then I can go to
you are
milk
just
after
concentrating
that.
on the X1. Yeah, you're just
X1.
concentrating on the labor.
Okay, got it. Thank you.
Any other question? Because I'm coming to ask you questions, so it's important you.
I wanted to ask Emily, is this in relation to both a DMU and a FEM?
Okay, so you see how in normal DEA, when you are doing calculations, you are doing it in relation to the DMU. Here we are going further into the DMU and doing it in relation to the variables. So you are going to, in each DMU, the number of variables. So let's say if you're having 3 inputs, 3 outputs, you are going to be doing the calculation 6 times for that particular DMU before you go to the next DMU and do it 6 times. Before you go to the next DMU. So for this one, it's just one variable. That's one input or one output that you are looking at that you do the calculation for.
No, my question whether it's for both a DMU and a FEM. Sorry, a variable.
No.
And I'm saying no, because it's one DMU and then the variables in the DMU is what you are doing the calculation for.
Yeah, but Emily, he's right in saying that when you are doing the analysis, it's not about one DMU and the variables in that DMU you are looking for. In practical sense, you are doing it for all of the DMUs. That particular variable. So if you take variable X1 and you are doing for that variable X1, it is a variable X1 for all each of the DMUs at the same time in real life. But graphically speaking, when you take one DMU, you are assessing how efficient each variable is inside that. But if you say you are doing that in real life, that's going to take long, Albert, isn't it?
Yes, Doc.
So your question is what?
Yeah, so me, I wanted to understand if what he's saying applies to only a particular DMU or like variables.
It's variables.
Okay.
But what make the variables? What make the DMU?
The variables.
So that's why I say, what's your question? It's the variables that make up the DMU. So what you are doing, you are not doing it for the DMU, you are doing it for the variable. But eventually, when you have done it for the variable, you can amalgamate them to for the what? For the firm,
For the
isn't it?
DMU. For the firm, okay.
Okay. Now, guys, why ideal? Did she explain how why ideal? By the way, when you are doing your own interpretation, this is what you do. You write a complex one first, then you come and use graph to prove. If they don't understand, you say, don't worry. When it comes to the graph, you understand. But why ideal? Emily, have you looked at the point 2?
No, Doc. Okay, so the point 2 says find the potential improvement points. That's the PIP, also known as the MEA benchmark. And you do so by using the IRP by moving the input and output from the ideal reference point to the MEA target. So this is done by solving just one linear problem, programming problem, whose result is now used to compute a vector of variable specific inefficiency. Okay, so like was said before, for the ideal reference point, that one gives you the ideal point that you would want. So it brings it down to the most minimum input. And then for the PIP allows you to draw it back to the MEA target, which is the realistic one. So ideal reference point can be irrealistic, but when you bring it back to the PIP, that one will be the realistic one that the DMU can try to achieve for efficiency.
Guys, there's no doubt that you are confused, true or false?
Doc, I wanted to ask if the ID reference point, if it is real or it is imaginary.
It's imaginary.
Okay, so it's
Okay.
imaginary. Okay.
It's imaginary in the sense that when you go to the company, you won't see it. But it's calculable. Do you get it? I'll give you an example. If a person's height is 5.9, then you know that it is possible that somebody can be 5.2. Do you agree with that?
Yes, Doc.
It's possible. Because you've exceeded already 5.9, anything inside is possible. I can imagine, that's why I say, I can imagine that somebody in the country can be 5.2. That is possible to imagine that. So it's imaginary. But don't worry, when we come to the hypothetical example, you will understand. So guys, once again, don't worry. When we come to the hypothetical, you will get it. That's why you should ask questions. If you are not asking questions, you are in trouble. Because it means that you are not understanding the foundation to ask questions. Okay. Let's look at a production function. But this one, we want to call it an environmental production function. Why environmental? Because we are going to consider a bad output. Another word for the bad output is undesirable, as you can see here. So we're going to consider this undesirable output here called bad output. Of course, yes, Ken.
Doc, please, with the MEA, we said that we are able to find out how efficient each variable is in the DMU. And with our work, we are doing a two-stage analysis. So the second stage is doing a regression analysis. So I wanted to ask if the
That second stage
regression
is different from
analysis.
the two-stage here.
The second stage regression is different from the analysis of the MEA.
Completely different.
Oh, okay. All right.
Because you guys are not even doing the variables. You are doing the thing. Isn't it?
Okay. Yes,
Uh-huh.
please.
You guys are doing the thing. You know, you are using basic DA. But if you after you've understood the MEA, you want to use the MEA, that's great. In fact, that will be solid. Ever. Because what you are going to do is that you're going to check what you are doing, you are checking how efficient is GCB, EcoBank, FB, and things like that. You're just looking at the firm. But what we are looking at is how efficient are the deposits of GCB? How efficient are the capital for GCB, the loans for GCB? How efficient is a fixed asset for GCB, for employees for GCB? Do you get a point?
Yes, Doc. All right.
And then after that, you can now say how efficient is GCB. So this one goes deeper. So the bad output in a bank, give me an example of a bad output in a bank. Anybody? Mention
A
it.
bad loan.
What?
A bad
Non-performing
loan.
loans.
Non-performing loan. Yeah.
Okay. What else? I know that's the one everybody knows. What else? Bad output. Bankers. Chris, are you doing banking?
Yes, Doc.
So what is another thing that is bad? Remember that undesirable output or bad outputs are byproducts of the good output. Okay, give me another thing that is a bad output in the real world, apart from banking.
CO2 emissions.
Apart from that, apart from pollutants, apart from pollution. Emily, give me one. God will give me one.
Doc, wastewater.
Wastewater. You mean the water we waste in the house?
No, Doc, like from mining. I should think so.
Why? Wastewater.
Okay, so I think forgotten the exact word, but is it like mine fields or so where they dump rubbish?
Oh, not just that. I mean, look at the home. When somebody is bathing and that bathing now, comes out and goes to do some dam in another person's house, that is a bad output. It's a waste water. Because that is a byproduct of the good water, and that is hurting some people. You didn't know, eh? Have you heard of bushfires?
Yes, Doc.
Is that good output or bad output?
Doc, it's bad output.
Yeah. Is it man-made or not man-made?
It can be man-made.
Can it be prevented?
No.
Hey, you can't prevent it.
Doc, it can be prevented.
I'm giving you examples that is not thought about. What other example come to mind?
Okay, so Doc, for mine, I was thinking in terms of like mining,
I know
how the waters are being produced. Okay.
I know. The only thing is that you were thinking deep from what you have read. But I want you to think outside what you've read. Who else has an example of a bad output?
With our body,
King.
With our body, could we say urine?
Yes. But the question is whether the urine is causing a problem. Is it a problem? When the urine are flushed out, is it causing a problem? Do you get a point?
Yes, sir.
If it's not causing any problem, then it's not really, it's an output. It's a byproduct, but and of course it's bad, but is it causing bad to somebody? But suppose the urine, whenever the urine comes, it goes somewhere, and then some people start smelling it. That's when it gets a problem. Get it?
Yeah.
Because the non-performing loans is a bad output because when people default, it affects the bank. It can collapse a whole bank. The pollution is a bad output because it's a byproduct of the production of cars or production of certain things. And it affects, it mixes with the air we breathe, and then it causes cancer and several things. It's a bad output because it has a negative effect when it is out. That's why sometimes we call it negative externality. Another one is boiler, refuse. When you cook food, okay, or you clean the house, the things you don't want, these are byproduct of the things you want. So you wanted the television now takes dust. You put it down. You bought some biscuit, you want the biscuit, but the biscuit now, the paper's in the kitchen. You cook some food stuff. So you buy them, you cut the potatoes, the cassava, and then you pack the rubbish, you put it in the bin. These are things you don't like. Now, why are they bad? Because they will pollute the environment if they are not properly handled. The same way CO2 can pollute the environment unless it's properly handled. So the same way non-performing loans can collapse the bank if it is not properly handled. So sometimes you use collateral to handle it. You use, you set up a certain amount of money in case the person defaults and things like that. But the key point is that until it is handled, it's bad. My American friend will say it's bad. It's really, really bad. So rubbish dump is another one. Now, let me just give you quite a funny one. You spoke about urine. Give me one thing that comes out of the human body that can be bad. Chris, what comes into your mind? Yes, Albert.
Fat.
Fat, that's it. You, Albert, things like this are what your mind can recollect.
Oh, no.
These things are what you remember the most. He doesn't remember, other things except these ones. Next time, I remember I do reference point.
No, I wanted to ask if inflation can be considered a bad output.
Well, it depends on how you look at it. I mean, Albert, Godwin, we've looked at this thing before, haven't we?
Like, I didn't hear the word he said.
Inflation.
Inflation out here.
Inflation is technically bad. To be honest, my guy was once upon a time modeling it as a bad output some time ago. But that would be a beautiful research to look at. So for those of you who are looking at energy and all of that, it's not really part of the energy situation. But God, you didn't consider it as a bad output, did you?
No, not part of my inputs nor outputs.
You consider it as a second stage.
Yeah.
So I mean, it would be nice to look at it as a bad output because it's just like go back to insurance. That's another possible bad output. Claims. When people are making claims, what are claims? And there's another one which is not claims. What is that? In insurance.
Is it the premiums?
Premium. Now, which one do you think the insurer likes? Is it the claims or the premium?
Oh, definitely the premium.
Exactly.
Premiums.
They want you to make the premium, but they don't want you to come for the claims. Why? Because when you go for the claims, it affects them. So claims can be modeled as a bad output. But then there will not be claims if there were not premiums. Do you know that?
Yeah.
So the claims are byproducts of the premiums, and they deplete the coffers. Depending on how the bank sees it, they deplete the coffers. And some insurance companies will tell you, "Oh, I don't have a problem with it. I don't have a problem with it." You know. But when you make the claim, you can see what happens. Okay, so these are examples of that. So note it. So we have an environmental production function here. And you got to always learn how to write the mathematics of this. You see, in your methodology, you got to document these things clearly. So this is desirable input, desirable output, and then undesirable output. That is a C. All of them are real positive alternants. Their maximum values are shown here. And it is produced in such a way that the X can produce both the desirable and the undesirable output. This is environmental production function. Okay. 3 assumptions underpin this joint production function. Now, why do we call this joint production function? Who can guess? Why do we call it joint production function? What is a joint here? What is a joint here? You can unmute yourself and start. What is a joint? Otherwise, I'm calling you. Joint production function. What is a joint here? Ben Susan. What are we jointly producing?
The outputs.
Yeah, what are they?
The good and the bad output.
That's it. The good and the bad output, they come along together. They don't, it's like twins. Once this one comes, this one is coming. It's coming. So that's why I say joint production technology. Okay. Now, so the first assumption is free disposability of output. What does that mean? Free disposability of output. Godwin. What does that mean?
It means there's a possibility to be wasteful. Increasing your input doesn't mean that your output should necessarily increase.
Again.
It means there's a possibility to be wasteful. That if you increase more input doesn't mean that your output should necessarily increase.
Okay. Give an example. Give a practical example.
Okay, so I'm going to come. Oh, sorry.
I should go and come.
Yes, please.
I like that. Okay. All right. So who will handle it? Who will handle that? Albert Kofi.
Doc, could it be the fact that it is
The way you started it. You're asking me a question rather.
it is unbounded. The outputs are unbounded.
You see, when you give some very complex terminologies and you don't understand yourself, that's what you're trying to do. Isn't it? You bring a very strong word that you yourself have to take some time to dissect when you ask, what do you mean? Anybody? Emily? Emily, quickly.
Sorry, Doc. Okay. So I think if we are using the graph to see, we
Emily, you talk a lot too much in graph. Talk in managerial practical sense.
Okay, so I think that this assumption is saying that for the desirable output in particular, you can reduce the desirable output, as in the desirable output can be reduced without having to incur any additional cost. So how to explain? What managers produce, the desirable output that managers produce can be reduced without incurring costs, additional costs.
Yeah, you're reading. Chris, what are your outputs? Be precise and concise for me. What are your outputs? Let me use that as an example. And please don't mention loanable funds.
Okay, my output, the desirable ones are loans and then earning assets, and those earning assets are investment securities. And then I have one undesirable output, which is NPL.
Okay, good. So let's take loans. Will banks want to increase loans or want to reduce loans?
They want to increase loans.
Good. So that means loans are desirable. Okay. Now, is it possible that even though the bank want to increase the loans, a particular bank will not be able to increase the loans and thereby will be decreasing the loans? Is that possible?
Yes.
And is that seen to be wasting or not functioning well?
Well, if that bank's NPL is high, he would want
Forget about
to.
NPL. I said that the bank is supposed to raise the loans. And then we check in a particular year, the bank didn't give any loans. Is that good or bad?
It's bad.
Why is it bad?
They are in a business to give loans to make profits or make returns on it. So if they are reducing in their key KPI, then it's bad for.
Good. So now that they reduce the loans, they should be punished, isn't it? Not that somebody is specifically going to punish them, but that should affect them. That should affect them. But then they do that without it affecting them. So what we're saying, what free disposability is saying is that you have the option not to do the right thing, and that should punish you, but you don't get punished. You don't get punished. You don't get punished in the real instant case. Maybe you are punished later, but you don't get. So you are allowed to be inefficient with your output production. You are allowed to be inefficient in the production of your output. And in fact, what is so beautiful is that bad outputs are feasible too. Bad outputs are also feasible. That is what this assumption is saying. Not just desirable, but also bad outputs are feasible. In other words, you can also generate non-performing loans as a bank. But you shouldn't, but you can. You can, but you shouldn't. You can. So that word free disposal, in other words, you are at liberty, free. You are at liberty to waste the input. You are at liberty to not produce, dispose the desirable output when you're not supposed to dispose them. Guys, that is assumption. The next assumption is weak disposability of the bad output. Weak disposability of the bad output, if you don't take care, it might confuse you with a strong or with a free. By the way, the free disposability is also the same as strong. Take note. The free that we looked at. Okay, the free here. You can say that strong disposability of desirable output. Okay, weak disposability. What does that mean? This one, I've put it here, right here. So you can just read it and explain. What is a weak disposability? Abdul Samad, you've not spoken today. You don't come to my class without speaking.
No, please, I've spoken. I said I'm now trying to grasp what.
Are you the one who told me about the discretionary and non-discretionary?
No, I think that was Keen. Oh.
Okay. No problem. You still got to talk. So get ready. Get ready and be learning the process. What is weak disposability, Emily?
Okay, so Doc, for weak disposability, here is stating that, let's take the example that he gave for the bank. So loans are good outputs, and then unpaid loans are the bad output. So it's stating that you can't reduce the unpaid loans without reducing the loans itself.
So why is the weak here? Why the weak here?
I'm not too sure on that.
So guys, the bad output are things you're supposed to reduce, isn't it? You all agree with that?
Yeah.
Okay. But when you try to reduce, it's rigid downwards. What does that mean? When you try to reduce, it's rigid downwards. What does that mean?
It doesn't like to be reduced, so it's
that's it. It doesn't like to be reduced. So our so the reduction becomes weak. Now, why is it rigid downwards? In this case, because that bad output is a byproduct, it's a joint product with a good output. So when you are reducing the bad output, hey, I won't go down. But if you want me to go down, then do what? What is he saying?
Reduce the good inputs.
Say it with macho. Naja rough, no?
You have to reduce the good inputs.
Yeah, guys,
good outputs.
you got to put yourself in the learning environment here. Okay, so you got to reduce the loans as well, the good output along with the bad output. Okay, because so if you want to reduce the bad output to zero, then you are as well going to reduce the good output to zero, because it's a production of the good that brought the bad. These are abatement activities. These abatement activities will usually divert the resources away from the good output. So why are we introducing this weak disposability? So Emily, that's why it's weak. It's weak because it's joint. We're telling them, Siamese twins. You can't cut off one without hurting the other. I get in the point.
Yes, Doc.
So we are introducing the idea that it is feasible to reduce the bad output, alone. It's not feasible to reduce the bad output alone. It's not technically feasible to produce only the desirable output in the absence of the undesirable output. It's not possible. They are twins. The only way to eliminate all of the bad guys is to end the production of the good guys. Therefore, it is weak. It's weak. It's weakly disposed. I think it's clear now. And then finally, the third assumption is that both good and bad outputs are null joint. In other words, they are there. They are producible. They are not empty. They got to be there. Unlike the desirable output, the pollution cannot usually be reduced independently. Pollution will have to come down with it. But they are all there. They are there. They are there. They are not non-zero. So let's go into the formalization now. Assume that we have a set of companies, DMUs. The DMUs number 1 all the way to N. Each DMU is a J. And the time period is 1 to T. Capital T is a total time period. Each T is one of the time periods. These firms are using M inputs, okay? And this is in a vector form, okay? So all of this is representing the input vectors. They are using that to produce the good output, the maximum of which is S1, and the bad output, the maximum of which is S2. So this is the technology, the environmental production technology that we have. What the MEA is going to do is that it's going to identify the ideal reference point. Now, watch it. You're going to see the model right now. The ideal, and if you can understand the mathematics, because that is the hardest of all our lectures today. The ideal reference point is represented by D star. D star. Guys, what do you think the D star is standing for? Well, you don't know yet, so don't worry. It's represented by D star. that D star is ideal reference point for the input. Write it down in your note because we'll come back to that. The D star is ideal reference point or the ideal point for the input. Then you have delta star. What is a delta star for? Godwell.
Okay, ideal for the output.
Ideal for the output. And then you have phi star. What is a phi star for? Kofi, Alex. How come I gave you the difficult one?
I'm not sure though.
I mean, if you look at the way the thing is going, if the D star is for the input, delta star is for the desirable output. I know he didn't mention the word desirable. What do you think the phi star was?
Hello.
Yeah, go ahead. Okay, Ben Susan.
What's output? Slack.
I said, watch the way we are looking at it. We are identifying ideal reference point. The D star is ideal reference point for the input. Delta star is ideal reference point for the desirable output. This phi star is what? Chris.
Undesirable output.
Is ideal reference point for the undesirable output. Take note, write it down. See, these same notes are what you use to write your methodology, just so you know. That's it. That's what you need for your methodology. All right. So we're going to solve equation 1, 2, and 3. Okay, we're going to solve it to get the ideal reference point. So that means that equation 1 will be for the input one. Equation 1 will be, formulating it to find the ideal reference point for the input. Equation 2 will be formulating it to find the ideal reference point for the desirable output. And then equation 3 will be formulating it for the ideal reference point for the undesirable output. You're going to do that for each input, for each desirable output, and for each undesirable output. You see, the undesirable output dimension is here, but then I went around and asked everybody. Meanwhile, the answer was on the screen. Now, this is non-orientation. Why is this non-orientation? Emily?
No, because you are looking at both the inputs and outputs.
Good. So we're going to solve this. Now, open your eyes whilst I show you the first one. So this is the input. We are solving for the D star. In order to solve for the D star, you got to minimize the D. We are not minimizing D star. We are minimizing the D. The D is that improvement factor for the input. The I naught means the specific input, the input and the evaluation. Because there will be 4 or 5 or many input. So that particular input you are dealing with, that's what is it. So this one will use input orientation. We are minimizing the subject to the weighted sum of the input, of all inputs, including the input and the evaluation, is less than or equal to the ideal reference point for the input and the evaluation. Now watch this. Then you say that there's another input constraint, but this input constraint is for all the other inputs, not the input you are assessing. So the input you are assessing there, that one is the what? The D. But the input you are not assessing at that time is the X minus. Take note. And this input you are not assessing, it is all of them excluding the one that you are assessing. That is why this thing goes from minus I, okay, all the way to I minus 1. That is the input excluding the input you are assessing. And then I plus 1 all the way to that, as many of them as possible. This constraint is very important that you understand. This constraint is what is telling you that what you are doing here is a minimization. After that, there is an output constraint, the desirable output constraint, which is this, and there is an undesirable output constraint, which is that. This lambda 1 is the convexity constraint. We call it the variable returns to scale constraint. And then this one, the lambda j positive, is a non-negativity constraint. The same thing that we get in linear programming. But the first two are the most important thing. So what this thing is doing is that it is minimizing the inputs, because you're going to take this D, then you now attach the D to that input, then you minimize each of the inputs under evaluation separately, keeping the remaining inputs. Okay, these are the remaining inputs, keeping them fixed, constant, whilst you are dealing with one of them for the time being. That is what this constraint is looking at. See the way I've gone through the interpretation. You understand it, and when you understand it, you don't fidget. You're explaining it. Of course, this R here means 1 to S1 is a total desirable output, starting from 1 to the total S1. And then the K is a total undesirable output, starting from 1 to S2. You have the convexity constraint, you have the non-negativity constraint for every DMU. That is this. That is for the ideal reference point. Now, suppose we calculate it and we come to realize that this X star, the actual value of the input, happens to be equal to the ideal reference. It means that the ideal reference is on the frontier. That is why it's the same as this. And that will mean that the potential improvement to be what? If this is the same as the frontier, if X is the D is at the frontier, it means the potential improvement to be what?
0.
0. It will be 0 because the actual value, okay, the actual value of the input happens to be the ideal reference point. So it means that the ideal reference point is on the line. Don't worry, we'll come back to this mathematics again. Now, the same thing you can do for the output. So you can see that here we are maximizing. Okay. And what is the difference between here? You can see that here you are maximizing, but then you have greater than or equal to the output. That is the ideal reference point for the output. Delta is the IRP for the output, the ideal reference point for the output. And then once again, you exclude all other outputs because you're looking at one output at a time. Okay. All other outputs are here. Then you have the input constraint. Before we had the output constraint, but now you have the input constraint, then the undesirable output constraint. Do you see something about the undesirable output constraint? The symbol. Do you see that? The symbol for the undesirable output. Godwin, what do you see about the symbol for the undesirable? You have done this before. Yes, Godwin.
Look,
What do you see? What specialty do you see about the undesirable output? Albert. Albert Kofi. Ben Susan. Any one of you. What do you see there?
Look, I can't see it.
I see
Can't see.
total undesirable output.
No. Emily.
No, please, the question is not that clear.
Okay, starting from the side here, the left side. What
Okay.
is it about the undesirable output here that is different from the rest of the constraint? That's my question.
Okay, dog is equal to.
Why?
Yeah, there's no inequality.
Why? Why?
Okay. Okay, so the constraint is saying that all other um all other undesirable outputs for the rest of the variables, except the no, I mean that one is not okay.
But
So
Albert, Godwell, I'm surprised though, because you have formulated this already in your work.
Look, I didn't really get the
Hey, you haven't
question.
done your formulation then.
No, I mean I didn't get the question well.
But oh, you didn't get a question. Well, Emily, yes, give him the question.
okay, so Doug is asking us what's different about the undesirable constraints compared to the rest.
Okay, yeah. So you mentioned the equality.
Yeah, and he's asking why. Why is it equal?
Well, I think that because it is still um,
That's why sometimes when people ask me that, the question is not clear. I know where the answer is coming from. It's not about the clarity of the question. It's about the understanding of the question in the first place. Okay, so first of all, it's because of the weak disposability, by the way. It's because of the weak disposability. You see, this output here is exhibiting free or strong disposability. Do you know that? Do you know that? Hello?
Doc, you are here.
I said, do you know that? I didn't say you are not there. Do you know that when we were talking about the assumption, we said that the output is desirable. The
Yes.
good output is desirable. Do you remember?
Yes.
That's this one. And then we said that the input is also desirable. We didn't say it, but you know that the input is desirable.
Mhm.
That is why that one is using it. Desirable here means that, we are reducing it. That's why you have less than. Okay. And then for the output, desirable means that we are increasing it.
Yes.
But then for the undesirable output, we ideally, first of all, we are not increasing it. We want to reduce it, but we don't have much control because it's a joint production. Do you remember? So we said that it's sticky downwards. That word sticky, Ben Susan, you said that the thing is not moving, isn't it?
Yes, Doc.
When the thing is not moving, what sign do you use for the thing not moving?
Equality.
Are you guys with me?
Yes, Doc.
Yes, Doc.
What do you understand?
Okay, so we are treating it as a fixed variable, so it's not allowed to change.
That's it. And because, not that we are treating it as a fixed variable per se, we are treating it that is weakly disposable. And because it's weakly disposable, we use that sign to reflect it. Now, that is a very tall assumption. I don't lie to you. Because the modeling technique doesn't do that. Well, you know what the modeling technique does? In our software, the modeling technique will still use the same principle as a less than or equal to. You get a point? So it makes it like we can reduce it. Do you see the point?
Yeah.
Just as we can reduce the input. If input were, labor, we can reduce input. So it uses that same principle. But you and I know that it's sticky downwards. And because it's sticky downwards, mathematically, it has to be this symbol. That is why, but there's a kind of slight assumption of why, I buy this one in the R software. The reason is because even though it's sticky downwards, because they know that they will be punished. I mean, the production. For example, if you know that you'll be punished for polluting the environment, so there's a tax you have to pay for polluting the environment. What does that do to you? Knowing
It
very well
makes you
that
conscious. Yeah, it makes you
You need
conscious
to
not to not to pollute so that you
exactly
don't
that
feel.
is what has eventually led to these electric cars. Because the car production do you know that recently all the car production companies are delving into, electric cars?
Yeah.
Electric version of the car. Toyota was never doing now Toyota is doing. BMW was now BMW is doing. It used to be the posh car, the Lamborghinis and the Rolls-Royce Phantoms and those things. But now these cars are going electric. Why? Because of environmental degradation. So there is a penalty, an externality cost. And that externality cost, because you don't want to pay, you are forced to reduce the pollution, the bad output. That is why I buy the less than or equal to sign. I just want you to know. This is technical, but you should know. But mathematically, this is a symbol. It's representing the weak disposability. Okay. Now, so this is a desirable output one, and then finally the undesirable output. You see here, we brought the equality there. We brought the equality even for its other undesirable outputs that are not in the evaluated one. We are still using the equality there. The input and the output are constant, as we know. So this is how you go through the formulation. Any question? So when you come here, okay, oops. When you come here, it says that by solving the models 1, 2, 3, the one I've just shown you, we can find the ideal reference point D star, delta star, and phi star of the evaluating unit. This one. Where the star here shows the numerical answer from the models. The numerical answer from the model. That gives you the ideal reference point. Now we go to step 2. Okay. We go to step 2. Step 2 is to find the potential improvement point. This one. The potential, the PIP, the potential improvement point. So watch this. You can see that now I'm adding the beta value to the beta value for the input to the beta value for the desirable output to the beta value for the undesirable output. You see it? I'm adding all of these together. Because now that you've done this, you are now going to the second stage. The second stage, I'll show you graphically what is happening in the first stage, what is happening in the second stage. So you maximize them. Now, why are you maximizing? Because you minimized and maximized and minimized. So now you've gotten an actual value that you are maximizing. I would have called it maxminized, yes. That's how I call it. But anyway, and now you are able to identify the potential saving from each input. You are able to get a target value. I'll come and talk about this. Okay. Because we are talking about input for now, that is why I'm focusing on this side. What is this XI naught? What is this XI naught? In real language, Ben-Susan, what is this XI naught?
The input.
What input? Be specific.
The desirable input.
No. No, yeah, but what specific input? Is it a targeted input or the actual input?
This is the target, I believe.
I know you're going to get it wrong. That's why I gave you that first. This is actual input.
Minus the, we're reducing. Yes, sorry. Yes.
So this is the actual input, and then we are taking out what? Emily, what are we taking out from the actual input?
Okay. Wow. Doc, so that one here, there is, Doc, I was going to ask you first about the B-test, the explanation for the B-test, because I forgot to. But inside the bracket,
the B-tests are the technical inefficiencies.
Okay, so that means that what we are taking out of it is the technical inefficiency, multiplying the actual.
Oh, you are telling me mathematics. I don't want that.
Okay, so the D star is the
Guys, the
value
one
you got
I've
from
written in blue is the most important thing. It takes us to the definition of the potential improvement, the potential efficiency improvement. Do you remember the way I defined the potential efficiency improvement from the start? Do you remember how we called it? We said is the gap, the improvement. Hey, Munkai.
Okay, let me
The
try again.
target
Okay,
and the
so
actual.
the one in blue is the potential savings that we can do. So if we subtract it from the actual, then we can get the MEA targets that we are looking for.
Good, but what is that? What is that? You see, that language you just used is also written here. What is that potential saving?
It was the excess inputs that was used.
And what are you doing to that excess input?
We are subtracting the excess inputs from the actual input.
Good. So guys, get something right. There is an excess. That excess is something that you could have saved. It could have saved you. But you have used it. It's an input. You have used it. You shouldn't have used it. You have wasted it. That input shouldn't have been used. You have wasted it. And therefore, we need to take that out so that we know exactly. Sometimes you come to the office, okay, and then we just waste time. That time you waste, we got to take it out of the actual work you did to be able to know, what you should have done. What you should have done. The correct thing you should have done. What you did minus what you did not do to get what you should have done. Very important. And so this is the excesses of the input. And of course, in the output sense, it would be the shortfall, the output shortfall that would have done. So note that this is the efficiency improvement, the potential improvement, which MEA focuses on. So that's why we say that it doesn't focus on the efficiency score. It focuses on your capacity to do what you could have done. And that is it. So when you take this one from this, you're asking what is the beta? The beta here is the inefficiency, the input inefficiency, the output inefficiency for the desirable and the undesirable output inefficiency. We don't know them yet per se. Don't be surprised. So we don't have the actual values. That's why they are not starred. Okay. But we know that these inefficiencies are supposed to be found. And once we find them, we'll be able to get it. My interest here is that this ideal reference point, it is far below the input. And if it is, unless it's zero, if it is zero, then this one is equal to the efficiency frame. But it's far below. So we are taking that out of the output, okay, multiplying the rest by the inefficiency term, and that will give us a potential saving. Then we now subtract all from the actual input again, and then that will give us the target. This here, the boxed here is a target. Okay, let's get into the simple example data set. Now pay attention here. If you can get this, we are done. So here, you see that we have these stars here. These are the solutions to the linear programming. Every time you do a linear programming, the stars are what you're looking for. Okay. So if you get the stars, the stars. But because we are going to focus on only the input, wherever you see the output, you drop them. So if we were to be doing input orientation alone, we will not need this one. We will not need this one. Okay. We will only need this one. And then here, we will need the first one and then not the second one for the second stage. This is the second stage. So take note of this. We'll come back to that. So the idea is that I'm now going to just look at input-oriented efficiency. So what's the first step? Keep this. The first step is to find the ideal point. That's step one. Chris, Albert, the first step is to find the ideal reference point for that DMU. But that ideal reference point is a point, remember, so it contains both input and outputs. Okay. The MEA, once we have gotten all of this, the input efficiency score, input specific or variable specific, I don't want to say variable because they are dealing with input. So input specific efficiency score for a unit A, look at the coordinates of unit A. We are going to show you how you compute the linear programming for unit A, assuming VRs. Unit A. Do you remember how to formulate it? You cannot formulate this because you are not doing it for the DMU. We are doing it for the input. But before that, before all of this, we are going to scatter plot the data. We are going to plot the frontier. We are going to show the radial and non-radial lines. Then we will identify the IRP. Then we will identify the PIP. Then we'll identify the benchmarks. Then we'll identify the inefficiencies. Then we'll identify the efficiencies. Pay attention. Pay attention. Let's start. So let's scatterplot the data. I'm sure you can all scatterplot this data. Emily, you type the Excel. Was it scatterplotted?
No, Doc, it was just the data points that was typed.
Chris, can you scatterplot this data?
Doc, in R or Excel?
Excel.
Yes, Doc.
Yes.
Okay. Chris, if you were highlighting, which one will you highlight to scatterplot? If you were highlighting.
X1, X2, and X2.
You mean you highlight all of them downwards, right?
Yes. Columns.
That include the
X1,
headings.
X2.
Will that include the headings called S1 and S2? Albert copy.
When you select it, it will give you the options to put it in where they should be.
So it's easy, isn't it?
Yeah.
Albert Bensusan, tell him whether it's easy or it's not.
Oh, Doc, it is.
Sorry?
Yeah, it's easy. You can just select the...
Albert Kofi, tell them whether it's easy or it's not.
Doc, it's easy.
You people, the last time I told you guys to do, how long did you spend on that thing? Were you even able to do?
Oh, yeah, we were able to do it, Doc.
Do you know how long I guided you left to right before you were able to do it, the thing?
Doc, we struggled a little.
Are you forgotten how you struggled to put the frontier there, to draw the radial lines, to draw all of those?
Yeah, that's true. That's true.
You are sitting here saying it's easy. The guy has said it, so it's making you feel like it's easy, eh? Even him, when we give him to him right now to draw it and show the frontiers and begin to show the radial lines, keke, you would have seen how long it would take him to do. Oh, Chris, we should challenge you. Albert Kofi, is he easy? Was he easy? You grandpa, they didn't even finish. You Albert Kofi.
Yes, it's true. Enough for.
You had about 30 minutes, you couldn't even finish the thing. Now today you are making it look like it's easy. Go and learn. All of you, go and learn how to draw these things. It's not simple. It looks simple on the surface, but it's not simple. Okay. So, you see it being done like this, like I've just done now. It might look to you that it's simple. It's not. It is not. Okay. So the first thing you would have done is do the scatter plotting here. Then you take your own hand and draw the frontier. This is an input orientation. Okay. Now watch it that I've labeled the thing as well. The A, the B, the C, the D, E, F, G have to be labeled. Now, if you look at this, I'm trying to estimate the efficiency of which DMU. Ben Sisan.
So A, so because I'm seeing A star and A prime. So A. Hey, no, these are variables. So we are looking at X1 for variable, I mean DMU A. Yeah.
I'm going to accept the exams. I've seen that people don't learn. Now, so I now understand why I took that exams. I'm going to do exams now for you people. Because exams will make you go and learn all of this. Now you do exams. So you said for A, right?
Yes, Doc.
Okay. So you plot for A and for the DEA. For the new guys that are coming, you are supposed to draw a data set and show how the DEA is estimated and show it with a line. So I have to draw a line and move it to the A. That line will showcase the distance to the frontier, which is A prime, and it will show the distance to the firm, which is A. That is how DEA is measured. It's actually the same as the distance. It's actually the target, that is the distance to the target, divided by distance to the actual. That is the same thing. I'm just starting with DEA before I go to the MEA. Any question on this? In fact, let me try and see if I can do a zigzagging. Because if I try to plot, I'm trying to see if I could have plotted it. No. I'm trying to have plotted it so that you would have seen, but I mean, you'd have seen them moving nicely, but that is not showing. So let's move on. So you started from A, watch it. So this is MEA coming in. So DEA will just take this side, the distance, it will take A prime divided by A. That is what DEA will do. So if I was to estimate the efficiency for DEA, it will be equal to A prime divided by A. That is OA prime divided by OA, the distance to the A prime divided by the distance, which is the same as O target, the distance to the target of the DEA, divided by O actual, which is the distance to the actual firm. Do you guys get that one?
Yes, Doc.
Yes, Doc.
Kane,
Yes,
do you
Doc,
get
I
that
get
one?
it. Yes, Doc.
Okay. Go and draw it for your own. If you are doing output orientation, do it for that. If you are doing input orientation, do it. If you are doing for both orientation, do the same. Now, if it was both orientation, it would have simply been something like this. Okay, the thing will go something like this. And then if you are doing for something like A, for non-orientation, you would have done this way and that way. So master it. Okay. Now, once you have done the DA, to do the MEA, this is how you go around it. You will draw a horizontal line from the A leftward. You draw a horizontal line from the A leftward until you hit the frontier. In this case, it hits the frontier somewhere around E. Then you draw a vertical line to hit the frontier on the X1 line. That's what you can see. Then you join the two zigzag Y till they meet. Guys, are you with me?
Yes, Doc.
Where they meet here, what is the name of that? Where the two of them meet, what is the name?
Like that would be the RIP.
No, use full name instead of
Sorry, ideal reference point.
Now, why is it called ideal then? In this context, graphically, you should now understand why it is called ideal. Why is it called ideal here? Abet Kofi, why is it called ideal? Yeah, Chris.
Because that's the maximum we can get to when we are referencing the efficient points.
That is the maximum or minimum. Which one?
Okay, input, so minimum.
Minimum what? Be clear.
The minimum improvement you can get if we are comparing it to the most efficient, which is E and then C. C.
Okay, please note that it just happened that it passed through that side. Okay. It just happened because if the firm was here, let's say if it was here, okay, and you were drawing that horizontal and vertical line, it would have gone this way. Okay, it won't reach E, it will reach somewhere here. And then this one would have gotten this somewhere here. It won't reach C. Okay, by the same process, you now goes to here. And then this one will also come down. And where they will meet, this will be the ideal reference point. Albert, are you with me? Benson,
Yes, Doc, I'm here.
let's set a question on IMEA so that you people can. So on the basis of this, now you can see that this becomes ideal reference point here. Now, this ideal reference point is ideal because that is how far the furthest point of input reduction for X1 and X2 we could have gotten. That's ideally, that is how we should have reduced the input. Remember, the input is here. In case you've forgotten, the input is right here. And our goal is to reduce it. This is how far we could have reduced it up to. Now that you've gotten this to this, now you draw a line from this corner here to that corner. That diagonal movement, you draw it to actually show, even though it's not a radial fraction because it's not towards the origin, it will now look like a radial movement. You would join the two corner points, the actual and the ideal reference point. So that would mean that if we were to be reducing the input from A, this is how far would have gone. This is how far would have gone. Would have come that far, that section. But this is ideal. It's ideal, but it's not attainable because it's outside the frontier. As you can see, the frontier is the yellow section. So it's only ideal, it's not, how do I put it? If something is not ideal, what is it? What is the opposite? I just want a better word.
Doc, I think we were using realistic.
Aha, very good. So this is idealistic. And then you now move it to the realistic section. So the next lowest level of the input you can do is to now move from this section now upward until you now bring it back. That is the second stage. So the first stage is going downward here. That's the first stage. And then the second stage is going upward. That is why we use the word first stage and second stage. Okay, now you're getting the point. So this is the first and second stage context here. But this whole thing is a mathematical movement, but graphically it's looking cool. So when you now move to this section and you get to this A star, not A prime, what then is the difference between the A prime and the A star? Who can tell me? No, this one, it shouldn't be Emily. Godwell, what is the difference between the A star and the A prime?
Okay, Doc, so you see that where the A star is, if I should map it downwards, it comes to 4.5 or so. Where the A star is, if I map it down, it comes to maybe 3.8. So the difference means that the A star gives you a more reduction. It's more a realistic reduction than where the A prime would have been. So it means it's giving you the best reduction that A can be respect to that input or the input.
So what is A star and what is A prime?
So
What are
A
they?
star is the MEA target you mentioned.
And
And
then,
then A prime is a DEA target.
guys, did you hear that? That is the word I'm looking for. That is a word I'm looking for.
So Doc, can you also put it as A prime is the radial and A star is the non-radial efficiency?
Sorry, say that again.
So I was saying A prime will be the radial and A star will be the non-radial. Can you put it
Yes,
that
but
way?
I don't want to say A star is a non-radial because there are so many non-radials.
Okay.
This is a particular non-radial, which is a MEA target.
Got
They're
it.
all targets. By the way, why are they all targets? You can tell me. Why are they all targets? Why are they all called targets?
They are all
Because they all
imaginary or
sit on the
virtual on the DMU.
they all
Sorry?
sit on the frontier.
They're all
Exactly.
imaginary or virtual DMUs. And
Yeah, but the
on
key is that they are on the frontier. Imaginary virtual DMUs on the frontier. Okay, but another name for the fact that they are targets could have been what? We could have also used what word instead of target?
Benchmark.
Benchmark.
Benchmark. Keep note of that. So that is a DEA benchmark here and A prime, and that is a MEA benchmark. If I draw something, Keke, for the output-oriented session and I ask you a series of questions in the exam, you should be able to provide. Now, so with that in mind, watch it. So we will move to this target, but there's something here. There's a gap here for this MEA target. There's a gap here. Okay. I'm not interested in the DEA gap. If I go up here, this is a DEA gap. I'm not interested in that because this is radial. But I'm interested in the MEA. You see this distance here? This distance is the potential improvement distance. Emily, that is your excess input. The input excesses that you spoke about.
Yes.
Because watch this. Why is it excesses? Because the guy is here. And ideally, he should have been A star at here. So he is using too many of this gap. X1 is using 4 to 5 to 6 to 7. How many units more?
3 units more.
3 units more. But technically, the thing is not at 4. You see that? It's not at 4. So it will not be exactly 3, isn't it? I get my point.
Yeah.
Okay, I just wanted to know because the actual section here will be somewhere here rather. So it is around 3 units of X1, which it was using in excess. What about the X2? Around how many units of X2 was he using in excess?
Around 1.2.
Around 1.2. Okay. So it was using these excesses. And we want to take them out. That is why you did that minus in the mathematics. So when you go to the mathematics, okay, and you get there, you will see that this minus here, that is the excess that we got to clear. That excess. Calculating the excess is not a joke. Because once you calculate the excess, guys, your job is done. You just subtract the excess from the actual, you have the target. Finito. And that is an exercise. So now you can see that this is the MEA target, DA target, and then now the MEA excess for the X1 is here. We call it X1 inefficiency. The inefficiency, that is excesses because you are inefficient. The inefficiency at the X1, and then the other one is the inefficiency at the X2. Take note that the key difference between the MEA and the DEA is that the MEA is selecting the benchmark A star relative to the IRP. Relative to the IRP. Whereas the DEA is selecting the benchmark relative to the what?
The origin.
The
Origin. That's it. Relative to the origin. Take note. This is super important. For those of you who want to do dynamic MEA dynamic MEA father of dynamic MEA. You should know this MEA before you dynamic it. You should be able to know, bring the dynamic into this picture. Where do you draw the dynamic part? Okay. But you should know this MEA. You're going to get this right after here. All right. So now, let's do the formulation. We're going to look at how we do for DMU 1, DMU A. We're going to formulate for the ideal reference. Now, DMU A has got how many inputs? How many inputs?
2 inputs.
2 inputs. So and remember that we do it for each variable, each input. So we are going to do the ideal reference formulation for input X1. Then we do the ideal reference formulation for input X2, or for DMUA. Godo. This is where we talk about put it into your work. Do you get it?
Okay.
You got it. All of you have to do a hypothetical example and formulate it like this, even including the cost people. So how do you do that? We minimize the D, because we are looking for the D star. The D, that is ideal reference for input X1 for A, with the intention of getting the lambdas, okay, from A to G. We are getting the lambdas, as well as getting the ideal reference actually. Now for A, how do we do it? We are going to take all of these input constraints, sum them, weight them. So you're going to have 7 lambda A plus 7 lambda B plus 5 lambda C plus 3.5 lambda D plus 2 lambda E plus 1 lambda F plus 10 lambda J. You add all of them, then less than or equal to that of the, not the input and the evaluation. Okay. Remember, if you can remember the formulation, less than or equal to that D star or the D. Okay. The improvement factor. And in this case, the particular improvement factor is for DMU1. This is for only the DMUA that we are dealing with. The DMUA. I've made a slight error here, but I hope that you could not see it. Which one is this? What should this one have been?
2.
Sorry?
2.
What is he saying?
That's
That
A.
A.
No,
Exactly.
one?
It's supposed to be A. All right. Anyway, that was just petty. Then you do for the other input. So watch here. What is the difference between this one? Sorry, this is the other input. Okay. So the other input, not input 1, X1. So you see that for input 2, you do it for all of them. Okay. But then you don't do less than or equal to the one you were looking at, the ideal reference you are looking at. But it's less than the A, the actual number. The actual number for the DMU. Now, this very one, if you go to the model, let me just go up to the mathematics. That is for this one. Okay. This one here, watch it. This one, this is the weighted sum of the input of the other input. The weighted sum of the other input. The other input, not the input you just looked at. The input I just looked at was X1. But now you are doing it for X2, the other. And for that, watch it here. You can see that that one, you're supposed to bring the input, the specific input and the evaluation. You should bring that number there. And in our case, that number was 5 for the A. Okay, so watch it. The minus I here, in our case, is going to be, actually, the 10 is not supposed to be A, it's supposed to be 1. Exactly as I indicated it. So this is supposed to be 1 because we are talking about input 1 and there are 3 inputs. So it's supposed to be input. Actually, it's supposed to be X1 or 1. It's the same thing. So I is equal to 1. I'm talking about this. I is equal to 1 for the first input. And then the minus I is going to be for the second input. Okay. That's it. And the minus I must have what? Must have a number for the one that is represented. But this one, you don't need to have the number for it because we are going to look for this ideal reference. And then you do for the output. So this is output constraint as usual. Okay. Then this is a convexity constraint and this is a non-negativity constraint. Okay. If we are doing output orientation or non-orientation, we would also formulate for both good and the bad output separately. Okay. But this time we are only doing for input orientation. But we are doing for input. So that's why I'm doing for only X1. And now I do for the X2 as well. Nothing changes. The only thing is I check here because I'm doing for the X2, the one that should be here is the X1. Okay. So the minus I is for the X1, input X1. Whereas the I is for the input X2. Take note. And the one you are doing for, because this one is for the input X2, that is the one that will have the D. And then the one which is a minus will have the actual number, in which case is going to be 7. Do you get some sense of this formulation? It's very important. Now, this is the first stage. What about the second stage? Mathematically, the second stage, you got to take this. Okay. Let's remember ourselves for this. Okay. This benchmark thing, remember it. You know this already. Oh, you remember I told you that the value here is supposed not exactly 3, but 3.1 something. Now you can see it. And then this one is not exactly exactly one gap, but it's 1.25. I had to go and calculate the thing in R before I show it. I'll show you the value in R. Okay. So now I have a question. Is the IRP feasible? We've already answered it. Okay. And the answer is that no, it is not feasible. It lies outside the boundary of the PPS. So the step 2 will bring it back. Remember the step 2 will maximize the beta, the percentage by which the inputs are reduced. And that will make the IRP possible and establish an MEA benchmark, what is known as the potential improvement point. We are going to do that now. So that is the second stage. We are going to find the potential improvement point. Please note that the potential improvement point is the same as the MEA. Take note. It's the same. It's the same as the MEA benchmark, the potential improvement. We are going to find this for the input, for the output, and for the undesirable output. We are solving equation 4. Remember the one that has a beta, beta, beta for the specific company. And then we use that to find the efficiency scores. Now watch here. So what you're about to see now is that we are going to find the benchmark, the MEA benchmark. But to find that, we find that along the diagonal path. I'm saying the word diagonal because we are going to calculate mathematically the diagonal. And so you all saw it in the direction of the IRP. Whereas the DE was in the direction of the origin. This one is in the direction. So we are down going upward to the target, the MEA target or MEA benchmark. We are going up, but in the direction of the diagonal path. So watch this. Now, because we are going up, we are maximizing. Because remember, ordinarily we came down like this. We got to the IRP. Now we are going up. When we're coming down, we're minimizing. And now we are going up. So we are maximizing. That's why you see that now this is maximization. We are maximizing the beta because it's a beta that will take us there. And watch this. This is beautiful, guys. This is beautiful. Watch this. You now still have the constraint for all of the first one, the X1. And watch this. You have the input. Because if you can remember the equation, Emily, your equation you had was the actual minus the x-axis, isn't it?
Yes.
And we saw that this was the x-axis. Now, the x-axis was also beta into brackets, the actual minus the ideal reference. Do you remember?
Yes.
Now, the question is that, is this 2 the ideal reference for that? Yes. When you go to the graph, okay, let me just go to the graph. That's why I brought the graph again. Okay. So when you check here, you see that at this point, I know the ideal reference point here. And the ideal reference point for the x1 is what? Is 2. For the x2 is what? Is 3. So now that you know the ideal reference, you start and put that into the equation. So it is 7 minus 2. The actual minus the what do you call it? The ideal reference. So this 7 minus 2 together with the beta, that is the excess. Yes, Emily, your hand is up.
Yes, Doc. Please, the objective function.
Yeah.
Can you explain why the beta is x2a?
So it's supposed to be x1a.
Okay.
Yeah. It's supposed to be x1a. Just a second. Let me just correct that because that was a very important observation. You see how when you are writing this code, okay, and you don't write it well, and you get to your presentation, you say, sorry, I was in a rush and things like that. You see it. It happens. So take note and go through them well. Okay. All right. So you get a beta for x1 here. So you get for the 7, the actual, and then when you go for the 2, okay, for the x2, that one too will be for this. Remember, you are finding the ideal reference point. You have the ideal reference point for both of them. It's 2 and 3. So you get the x-axis for both of them, and this is going to be the x-axis for both of them, and then the actual for both of them. Okay. And then the rest is just easy. The output constraint. Okay. And you can see that I didn't bring the undesirable output constraint, but that could also be there. It's not even in this model at all. So I tell that because I'm doing input orientation. Then your convexity constraint and then your non-negativity constraint. This is it. Now, we are going to do this inside the R software. We're going to do this inside the R software. And to do that, and by the way, this very one here, what is the name of all this? We had a name for it. What is the name of all that?
That's the target.
Albert Kofi. Albert Kofi, you would have said the same thing, wouldn't you?
I would have, yes. I would have.
What are you two know? I would have.
What targeting you?
No, because you are the one going to extend on this.
Yeah.
If you are going to extend on, and I don't target you to learn it, who else is going to learn? Okay, I have to ask you and Chris, you're going to extend this thing.
Yeah.
So if you don't understand the basic, how do you extend it? The foundation has to be, solid.
Exactly.
So I'm letting you know that you got to learn these things.
Yeah.
Because we generated all these things that you are seeing here from journal articles who didn't have this. We have to understand what they are saying, then create our own hypothetical, then formulate it like this. This is key. Okay. So once you have this, this whole thing that you are called MEA target, there's another name for it. What's the another name? Albert, what's another name for this MEA target?
Benchmark.
Yeah, benchmark, but there's another proper name in connection with this whole multi-directional efficiency analysis. Ben Susan. What is the name?
Yeah, target is what comes to mind.
Emily.
Look, the potential improvement point.
That is what you should all write down. The potential improvement point. The potential improvement point, the whole of this is the potential improvement point for X1. And the whole of this is the potential improvement point for X2.
Okay,
This is,
Doc, please question.
yeah.
Okay, so in the formulation, I know we had the inputs, outputs, and then the undesirable outputs. But the way it was, it looked as if you are looking at the X1, BMU X1 for X1, you had the first one for the input where you had to subtract the excess from it. And then the second one would have been for the other inputs with just its value, which I thought was going to be just 5 in order to find for X1. And then when you come to X2, you have one with just 7.
That one
The
was,
first.
what you are talking about was the first stage. Let me go back.
Okay, so in the second stage, you combine everything.
Exactly. So in the second
Okay.
stage, you are combining.
Okay, I get it now. Thank you.
And I think that because in the second stage, you're even combining, this value is supposed to simply be XA instead of X1A. You know,
I wanted to mention.
anytime you want to mention it, mention it. Because that is when, you know, because the left-hand side itself is that. The only difference between this. So this value is supposed to be exactly like that because it's just for A. It's the input for A. Is an input for A. Now, of course, you are finding it for individual, but then at this stage, you are combining mathematically for both of them because it's going to peel off for each one of them in the process. So you are determining the inefficiencies along the line. By the way, this beta here is the inefficiency. So this inefficiency term is telling you by how much the inputs were increased that they shouldn't have been increased. Okay, so the potential improvement point here, this potential improvement point is the actual here minus the beta. The beta is what you see here. And then the actual input minus the IRP or the ideal reference point. And all of those terms have been explained here. So if you want the potential improvement point, it will be 7 minus the beta. If you know the beta, it's the same beta both of them are going to use. Okay. That will give you these values. So these values become the MEA benchmark or the potential improvement point for input X1 and for input X2 as far as DMUA is concerned. I'm just doing A, but the software will give us all. Okay. Now, guys, I want to pause here and then we go to the R. So go to the R and then let's quickly run this code. Let me clear the screen. Open your R, follow the principle, understand the game, else you will be not clear. You see, the thing is that, let me close this thing and open it again. The thing is that if you, okay. I'm here to show my screen. If you don't understand these codes, you will struggle when you're doing your own. So it is critically important that you understand the codes. Okay, very important. Okay. So I think I gave you the codes, didn't I? I put it on the page.
Yes, Doc, you've given us the codes.
But those of you who don't have it, ask about it on your respective page so that Emily will send it to you. But I'm sure you all have. We are going to just run these codes quickly. And then even if we are not able to find the PIP, I'm okay. You should be able to learn how to draw these things. Okay, so the first thing is go to your Excel and then copy your data. Let me just show you something. So I'm here. This is my data set here. I'm copying the data set. Hold on. I'm teaching now. Okay. All right, guys. So you have copied the data. I'm sure you've all copied the data, haven't you?
Yes, Lord.
Have you all copied the
Yes.
data? Okay, you have the code. So we run the first code. Follow me. If you don't have the code and the data, say it all. I know you are going to say, oh, I'll do mine later. All right, so you run the benchmarking and then you load your data. I've just loaded the data. To see that the data has been loaded, highlight the D1 and you can see at the bottom that the data has been loaded here. So here you have your X1 and X2. Output has been normalized to 111 so that we can focus on input. The next thing is to convert the first column. You see, the first column is DMU names. Okay, so we want to convert that to replace the 1, 2, 3, 4 so that it will replace the row names and label the new data as D. Okay, and then the D will now, when you rerun it, it will now, the D will replace the column 1 with the row names. Let me show you. So I run this command here, show the D again. You see that it has replaced you see, it removes the column. It removes the column. So now column A is not there. And then you go to the next command, the row names, and then you go and run D again backward. You see that the A has now been replaced, has replaced the numbers. That's exactly what I mean. So you can see that now the data has replaced. So now, instead of using 1, 2, 3 to label, it is going to use the A, B, C to label. Then you now create your column binding of the input. You column bind all the input vectors here. Let's run that. You column bind the output vectors. We've done that. If you want some question about DEA plot, you can do this question and get some help. It will bring the DEA plot with a benchmark in there. Now watch the first one. We're going to show the isoquant. So this will show the isoquant for X1 and X2, as you can see, beautifully, scatter plotted together with a frontier drawn. Then let's add text. So I added the text to each one of them. As you can see, the texts are showing clearly those that are efficient and those that are inefficient. At this stage, in terms of DEA, we know those that are efficient. Ben Susan, which ones are efficient? No, which ones are strongly efficient?
So strongly efficient would be between E and C.
No, I said which ones? I didn't say between.
Which ones are strongly efficient? E and C.
Sorry?
E, C.
That is wrong. Chris, which ones are strongly efficient?
FECB.
That is wrong. Albert Kofi, which ones are strongly efficient?
So it's ECB.
That is wrong.
Okay.
Godwin, which ones are strongly efficient?
Doc,
CB.
E and then C.
That is wrong.
CB.
Emily, which ones are
CB,
strongly
Doc.
efficient?
Doc, it's just E.
That is wrong.
Hey.
Okay, because
You guys are overthinking now. Now, if you are left to talk Chris Zanu, which ones are, Chris hasn't even been here. King, which ones are strongly efficient?
Doc, F, E, C, and B.
That is wrong. So the thing is that if your lecturers are wrong, how come you won't be wrong?
okay, there's no strongly efficient. Is that
There
what you're
is.
saying?
There is.
Because based on
Don't
the
because
previous...
you let's finish. When we
Okay.
finish, who is the next person I haven't called? Chris Zanu? Oh, he's not gonna get it. Chris Zanu, are you here? Are you here or not? He's even off. This guy has been joining and leaving. So the strongly efficient are F, E, C. If you ever mentioned that and I didn't see it, let me know. Now, you can't say that C is not strongly efficient because B would wish to go to C. And you can't say that F is not strongly efficient. F is still strongly efficient. You remember that question I asked you, Emily, the reason why you got the E to be wrong is because that thing I told you, I asked you the most strongly efficient, if you could remember. I did not ask that the thing is strongly efficient. That one, I was pinpointing those that were most. If I had asked you which one was the most strongly efficient, it wouldn't be this, it wouldn't be this, it would just be E. And for those of you adding B there, I don't know where we're getting that from. Because B is on the free disposability line. It's clearly dominated by C. So it cannot be. Anyway, let's move on. Keep learning. It's important. Keep learning. It's important. So now we go to estimate. If we're to do DEA, this is it. I'll just run this command 10. Okay. And then I'll run this and I'll get my DEA. So you are now able to get a radial line for each and you can now estimate the distances. I'm sure you all know this. But I don't want to do the DEA. I want to do the MEA and I want it to look good, beautiful. So you know what I'm going to do? I'm just going to start from the beginning here and just show the text again. Okay. Now I'll go to plot the DEA number 9 command again. And then show the text again. And instead of running for the DEA, I come down and run the MEA lines. Watch this. So you see that the MEA has drawn automatically. A lot of thought goes into this coding. And so you got to learn from this. Because when you're doing output transformation, you can do it, but it's not going to be exactly like this. And those of you like using ChatGPT and all of that, chat has failed in this. This is brand new. So chat has failed. So you can see that now, has it been able to help to identify the potential improvement point in this? Where is the potential improvement point?
Okay. Doc, that's where the green line dot is.
Okay, where
So
is
between...
Good. That's fine. That's fine. Where is a ideal reference point?
Where the arrow ends.
Where the arrow ends.
The mark of the arrow, yeah.
Now I have a question. What was it trying to, and this is very important. This graph, did it identify the DEA fashion? Did it identify the radial movement represented
Yes.
by what?
Yes, Doc.
The red
The
line.
red line.
The red line.
The red dotted line.
Okay. Did it identify the movement in the direction of the IEA, of the ID reference?
Yes.
With
Yes,
what
the
line?
blue dotted line.
Arrow.
Not
The
Blue
arrow.
dotted
dotted,
line.
the faint dotted black lines.
No,
Or
The
is it
blue
dotted or
dotted
not?
The
line.
blue line.
the blue dotted line. Very, very important.
Okay.
So you should know that it is thinking about the movement before it identifies the movement, because you cannot get that arrow line until you have gotten the dotted line. That's what I want you to take note. The arrow line is emanating from the dotted blue line. And that is how it did the calculation there. Now you can also do for another DMU right here. Right here. We did it for A. Let's do it for D. What do you do to the code? To do it for D, what do you do to the code 13 here?
Doc, you changed the 1 to the input for D. So D should be, I think, 4. So you are going to change it to that.
Good. So when you go up here, you will see that the DMU-D was numbered 4 here. So the DMU1 is a one that is showing 1, 1 for the MEA lines. So if you change this one to 4 and you change this one to 4, you can do the MEA calculation for D. That's what you see here. So it's done it for D here. Okay, you can do it for G by changing it to what? 7. So if you change this one to 7 and you change this one to 7, you can also run for G. So you see, he's calculated the MEA. So you'll be able to know the ideal reference point for each of them. I did it for those ones because those ones are truly inefficient. When you go and do for the others, you will not have much lines because they're already on the frontier. That is how you graphically generate the score for this. Now, last thing before, because I don't want to do the calculation yet. Where is the okay, so let's start generating some results, okay? Because that will be interesting coming. If I can finish this, that's even better. So now we can proceed to run the efficiency estimation for DEA. This is for the CRS and for the VRS. Look at it, code 15 and 16, okay? Now, for the CRS, the retention scale is 3, okay? And this is all input oriented, so that's why you see input. For the VRS, the retention scale is 1. So let me run the 2. And then I do the same thing for the MEA. For the MEA, CRS, it is 3, VRS is 1. But then to indicate that it's MEA, I do MC. Then I'm also going to show the efficiency scores and I'm also going to show the beta values, which is the inefficiency scores. Okay, but this time I'm going to do for both the DE and MEA, and I will show a data frame for the results. So I'm running all at a go. Look down. So that's it. You see down there, you have the data frame for the results. These are beta values. Do you remember that when we went into when we're calculating the PIP for A, we use this 6 point, MEA, we use 6.625. Do you remember? Let me just go back and show you. Do you remember here? We use this 0.625. Are you guys watching? That 0.625, that beta value, that is the value you just got here. That's the value you just got here. Remember that the constant and the variable returns are giving you the same scores in this case because you're in the same domain, the same portion of the PPS, but technology set. Now we can calculate the lambdas. The lambdas are the weights when we use them to get the benchmark. So we are calculating the lambdas here. Okay, run that. Then we can calculate the PS and the slacks. Both PS for the MEA, slacks for the DEA, all of them, we are doing it. And now we will come to the most important part, the step 1. The step 1 is to identify the ideal reference point. Now, I told you that you need to calculate the horizontal and the vertical distances. This one, 37 here. Calculate the horizontal and the vertical distance. That distance, remember that 3.13 and the 1.25, that distance, we need to calculate it first because it's a distance you're going to use to find the potential saving, the excesses. So this is a distance. Watch the result. So look at for the firm. See for firm A. The distance is what? For the input X1, the distance is 5. So when you go to here, when you go to A here, okay, and then you move from here, that section here, which is 7, and then you are going down, remember it comes all the way to this section here. What is that?
Doug, can you please reduce some of the lines there? It looks
I know.
it looks very complicated.
I know. Okay. Let me just clear some of these things because I have them already, I don't need to use this one. So let's go to the slide here. This one is better though. Okay, so you are starting from A here, 7. Okay, you are moving all the way to the IRP, the distance from 7 to IRP. So remember, from 7 to IRP on the X1, that is what? 7 to 2, isn't it? Do you realize that?
So, yes.
Guys, follow me. Oh. When you get lost, then you don't want to follow again. So from 7 to 2, the gap there is what? Is 5. So that is why when you come here, you are seeing that the gap for the X1 is 5. Now let's go up here. We are moving down horizontally, vertically from 5 to 3. So the gap is what?
2.
The gap is 2. 5 to 3. The gap is 2. Okay. Yes. So that gap of 2, that is what you are also seeing here for the X2. For A. So that is a horizontal. It's called MV direct. MV direct. Once you have the direct, you just multiply the direct by the beta. Remember the inefficiency term we spoke about. And that will give you. You see, this direct here, there's something you don't know about this direct. This direct here contains that thing. That direct was the, you remember we had 7 minus 2b before we multiplied it by beta. Do you remember?
Yes.
That 7 minus 2 here is the 5. The whole of the 7 minus 2 is what we call the direct. That's a direct here. That is a dollar direct. Then you multiply it by the beta. The beta is this one. Is a ME inefficiency. So when you do that, the 2 will give you the excesses that you have been talking about. So that's what we are going to do now.
Okay, so that since it's the inefficiency, why is it dollar efficiency rather?
This one.
Yes.
Since this is inefficiency.
Yes, that's the beta.
It's only a terminology. So what it means is that the value is coming from the efficiency assessment. It doesn't mean it's coming from efficiency score, but the whole multidirectional efficiency assessment.
Okay.
Yeah. So that is it. And by the way, this MV, as for the MV, you know, I used it.
Yes.
I created it. But this one is coming from the model itself. So when you multiply the 2, this is what you get. And then, so that will give you the potential savings. But what do we want? And by the way, that's for the ME, for the Farrell. For the Farrell, the potential saving, the way you calculate it is this. We are not too interested in that. And so now we can get this score, the potential savings for the MEA. This one, let me just show you first. So you see now, we have the excesses, the potential saving for the first one. This was a 3.125 that we saw in the table, if you can remember. Okay. That is the exact target. Sorry, the savings, the one you removed before you get the actual target. I mean, let me just go back here and you can see that here. Okay. So the potential savings before the target, before this target, this one was a 3.125 here. That's what you see here. And then the other one is a 1.25. Okay. So this 1.25 is from here. Is this gap here? Is this gap here? So that is towards the end year. This is important for you to know how the whole analysis is generated. If you are doing yours, all you have to do is to put it in my code. So once you get these scores, you are now done. Let me plot the entire result. The entire result is going to be something like this. Okay. It's going to be something like this. And I'm not so much interested in any of those things because it's producing slacks and everything. But the most important ones are these ones here. Okay. The ME direct, and then for the potential savings. The potential savings, we are not interested in this. Where is that? We are interested in, you see, the actual names that then come. So if you don't take it, you won't see. Okay. So the actual names are this last one. So when you check the actual score, let's go back here. If you want the actual score here, if you look at this target, okay, and you want the actual score, what is it going to be? The distance is going to
3.8.
exactly
And
3.8
then
something.
4. Yeah.
Yeah. It's not exactly 4, but something there about there. So that is going to be the exact value that you get. Okay, let me close this and then continue to the end. So the optimal solution. Now you have to find efficiency scores. Okay, guys, watch it. Once you have all of this and you've gotten these excesses and pulled out the excesses, you already have the actual. Subtract the actual from the excesses, and that gives you the target. Now that you have the target, you see that target is this one. This whole thing is a target. Is a target. So this is the actual minus the excesses. That gives you the target. So the target now divided, let's call it T, divided by the actual. The actual is a 1 in the denominator. That will give you the efficiency score for each one of them. Now watch the word I'm using. I didn't say inefficiency score. I say efficiency score. So for input efficiency, you get this. For output efficiency, you get that. And for the bad output efficiency, you get this. That is it. And you can do a similar thing for those of you doing the slack based. Okay. Now, when you get this efficiency score, these are mathematics. But how do we get them? Once you have all of this efficiency, you can drop them here. Okay. You can drop them here, and then you'll be able to get what? The overall efficiency. So you can see that the overall efficiency is taking the input score, okay, then the desirable output score, then the undesirable output score, then that's it. But if you are doing only input oriented, you just do the first one. Then you are sorted with that. That's mathematically speaking. Okay. What about solving it? And then you can also get the input efficiency, from here, the overall input efficiency. This is the same thing as that, but this is it. You can use that to develop the input efficiency. And then you can even use that to develop the MAM quiz productivity. I have that one on the right here. But first, let's find the final input efficiency score. I'm going to this data set, and I'm just going to copy the course. Okay, I gave you the course. Oops.
Doc, we have up to the slack.
Okay. So one thing about, and maybe I need to just send you this. One thing about this is that when you get the direct, because the direct eats up, it's mixed together, you got to peel them off one by one. Okay, so check the code I've sent you. So you are going to create for each input, because the direct comes together for input X1 and X2. You got to peel off. So you can see that here, I'm removing the second column to get for only the first column, the X1. Then the second one here, I'm removing the first column of the direct so that I can calculate the excess input for the second one. Because I have to calculate the excess input from the IRP and then add it to the actual to give the IRP. So that is the second one here. Remember that the ideal reference point, I've told you the ideal reference point is the actual input minus the excess input. That's it. That's ideal. The actual minus the excess. The actual minus the excess. So you are taking the excess from it to be able to get the actual. So we now have to get a new ideal reference because I've peeled them off. Okay. So I get an ideal reference, brand new ideal reference for only input X1, which is this, for input X2, which is that. Now let's look at the table for that. So you see now, I have my ideal references for each variable. It's 2 and 3. When you go to the graph, you see truly that is 2 and 3. When you go here, okay, watch. The ideal reference is truly 2 and 3. Okay, exactly as it is. And so now we are going to use that ideal reference to do the next calculation. Once you get this ideal reference, I've sent you that code though. We can now wrap it up with the second stage. Because remember, the first stage is finding the ideal reference. The second stage is this. So we are going to move the input and output from the ideal reference to the target point. That's the last thing we are going to do. And what are we going to do to get? We are going to do that to get the, what do you call it? We're going to do that to get the PIP, the benchmark, the MEA benchmark. The PIP is defined as the actual minus the beta. We've done it. The PIP is a target, okay? The actual minus the beta. And we know that the beta is an inefficiency. So to get this PIP, I'm now doing PIP for each input. Each input. So watch this. This is it. So the potential improvement point, which is the same as the target, guys, once I get a target, I'm done. Because once you get a target, you divide it by the respective input and you're done. So for the first one, you're going to get this. For the second one, you're going to get that. Now let's create a beautiful data frame for the two of them. So watch it. I'm rounding the data for all of them here. Let me close this so that you can see it better. Okay. So watch. I'm drawing for all of them, but I'm interested in the this one is not even important. Okay. This one we've done it already. It's the last one here. So look at the last one. I have the PIP for the first input, and then I have the PIP for the second input. Emily mentioned it correct for the A. She said that it's going to be 3.8 something. And then she also said that the second one is going to be 3.8 something, or in this case, 3.75. So for DMUA, the potential improvement point, the MEA potential improvement point for X1 is 3.87, for X2 is 3.75. What do we do with this? Simple, divide it by the actual, and you have the efficiency score. Let's wrap up with that. So we are going to use this one. Again, I need to send it to you before I send it to myself. You go here. Oops. Good. And so we now have the relative variable specific efficiency score. Look at the way I've defined it here. I've defined it as this one. In fact, let me use square brackets here. It's the whole of this one divided by the input. That's it, and you're done. So I take for the efficiency, it's going to be the whole of this one divided by the input. That's it. Then you take the second one. For the second one, input x2 is going to be the whole of the PIP divided by the input. Now watch it here. You can see that I'm writing this, but I could have also used the PIP because I've already written the PIP up there. Okay. So these two that I've written, if I show you the first one, you see it. You see the efficiency scores. Okay. Oh, this is inefficiency scores. Okay. This is inefficiency scores. But then the efficiency scores is 1 minus the inefficiency, or what I said before, the PIP. Okay. The PIP divided by that. This is it. Okay. It says that object X1 not found. Where is my X1? Oh, okay. It's not supposed to be X1. It is supposed to be DX1. Let's see. Let me just do this. The efficiency the input variable, I'm just changing it. Yeah, it should work now. So watch. If I go to this very first one and I show the efficiency score, you can see that for DMU-A, it is 0.55, okay? I do the same thing here. I run this one. I show the same efficiency score, should be the same thing. There you go, it's the same thing. So these formulas are the same. They are the same. Guys, when you are doing yours, you have to just ensure that. So this very example, it should have been dollar, D dollar, because it's coming from there. So instead of just X2, should be D dollar X2. And when you do that, let me separate them so that it doesn't confuse. D dollar X2. Okay, you run this one, and then it should be the same thing as that one. And then let's do for the EF2. EF2 also be the same thing. That's it. And then it should be the same thing as that. And then when you're done, you can now find the final answer here. There you go. Look at the final answer. In fact, this last one, I just need to go to the notes here and just edit it because here was an explanation. If you don't understand, you can raise your hand and ask. So all I'm doing here is I'm just rerunning this and then indicating that it's the same as that. It's the same. How do I put? It's the same thing here. It's the same as that. And then this second one. The only thing is that you just change this one to $2. And then this becomes the same score. So that would be for the efficiency for the firm one. The efficiency score for the first one, and then the efficiency score for the second one. I'm just using different colors for them. And when you run that, you get, I mean, if you have been following me and you have done it, let me know. So that is it. Look at the final efficiency score for A. It is what? 0.55 for the X1 and 0.75 for the X2. Do you know what is so dangerous about this? If we had used the DEA approach, the DEA would have said, let me see if I can bring the DEA efficiency scores here. Yes, Albert.
Doc, just to double check, I think for the EF2, the DX, we used 1 instead of 2. So just
which one?
check in. The one, so 65, line 65.
Yeah.
Is the D dollar, is it supposed to be X2?
This one is supposed to be X1. Sorry, X2. Okay, good.
Yeah, okay.
Okay. So I just want to put the result for DEA here. Okay. And then we see some bit of comparison. Okay. So I've just brought the DEA score here. Look here. DEA score. Do you see the efficiency score is what? 66 for A. 66 for A. But, is that efficiency score? Hold on. No. That was a...
Yeah, I think it was a VRS efficiency score.
No. I think it was a... It wasn't efficiency scores, you remember? It wasn't efficiency score. It was the beta, the inefficiency term that we did. I think we didn't calculate efficiency score for that, did we?
We
That's
did in
this.
the beginning. Yeah. Look, it was even is the efficiency for VRS.
Okay. But then the MC is not for the ME efficiency score.
No.
Okay. Yeah, okay. So now watch this here. This one here. In fact, my whole story is going to be from here. So when you see the D efficiency score is 66%. But when you go deeper, you see that input X1 efficiency was 55 and input X2 efficiency was 75. So even though the DA is saying that efficiency score is 66, majority of that efficiency was being contributed by what? Input X2. Input X2. Okay. Majority was being contributed. And look at this one. This one is even shocking. DMU, the entire DMU is efficient. But when you look deeper, you see that the input X2 is what? Inefficient. It was input X1 that was efficient. Sorry, input X2 that was efficient. So if you had not used the MEA, you would have wrongly concluded that the firm is what? Efficient. When you go deeper, you will see that, apparently it was only X2 that was exhibiting the efficiency. But X1 is exhibiting inefficiency. Now, when you go to DMU3, it was said that it was efficient. You can see that here, C is truly efficient. Okay, and truly, both input X1 and X2 are efficient. Okay, when you go to 5, it's still efficient like the next one, like the 3. When you go to 6, it's also the same thing. By the way, the 5 and 6 are these two. That is why I told you that they are strongly efficient. Okay, those are the strongly efficient. And then the last one is G. Look at G. G is seriously bad. So when you go to G, the efficiency is what? 75%. But when you go deep down, you will see that much of that efficiency was as a result of X2 efficiency. X1 was 47%, very, very bad. So by looking at the MEA, you are able to identify what are the variable contribution, which variables are actually contributing towards efficiency. You are able to fish them out precisely and perfectly. And that is the beauty of this. You're able to see the variable efficiency scores all through and through. Now, of course, it doesn't mean that you cannot find the final efficiency score. You can still go ahead and calculate the final efficiency score, the overall efficiency score. You can still calculate it. And that is this one here. Okay. So watch this. I'm just going to give you the final code for calculating the overall efficiency. And that is this. And then you even compare the overall efficiency with your own, with the normal DEA. And you see something interesting. Let's go to the final gap there. So the overall efficiency for the MEA, see now I've put the input efficiency and the output efficiency together, all of them combined together. Okay, let's do that. And then let's add it to the table. And this time I'm going to add the DA one also here to the table because previously it wasn't there. So overall, the DA one is here finally. There you go. So guys, this is the final beautification of the result. So look at the DA efficiency. It is 66%. Then if you look at the MEA efficiency, it is 65%. So the MEA is a bit more discriminatory. When you look at it, MEA is generally discriminatory. Okay, generally, MEA is more discriminatory, just as the SBM is discriminatory. Look at this one. It's generally discriminatory. For those that are inefficient, it is generally discriminatory. For those that are efficient, yes. Even for those that are efficient, look at it. Look at it for B, because B was exhibiting slacks. And because those slacks were incorporated, you can see it here. Because those slacks were incorporated, you can see that it has been penalized for belonging to the free disposability section. Very good. Ladies and gentlemen, now I want you to look at the conclusion. What is the final conclusion to all this? Well, this is the final table. MEA answers the question, what should improve? SBM will tell you how much slacks exist after accounting for inefficiency. SBM projects the DMU directly onto the frontier. That's what SBM does by eliminating the slacks at the same time. But what the MEA does is that it allows every variable to move in its own direction. So let me ask you a final question. What happens to the slacks in the SBM? Godwell, what happens to the slacks in the SBM? Emily, what happens to the slacks in the SBM? What happens to
the question is not clear to me.
Okay, doing the SBM calculations of everything, what happens to the slacks? Chris? Final question. The slacks are incorporated in the efficiency score of the SBM. What happens to the slacks in the MEA?
Like it's also incorporated.
It is also incorporated. Okay. It is also incorporated. So what then does MEA have that SBM doesn't have?
Okay, so the advantage of MEA is that it's looking at the variables individually. SBM does not have that.
Very good. But you didn't know that. You didn't know that the SBM also does variable specific, just like it wasn't the focus.
Yeah.
That is the one that maybe, just maybe, we got to write a paper on. That is the one maybe, if Chris is gotten the time, he can rather venture into. But regarding the benefit, the difference between DEA and MEA is clear from here. Okay. DEA will give you an efficient unit of 1. MEA will give you an efficient unit of 0, technically, until you convert it and manipulate it. DEA scores are easy to interpret. MEA scores are hard to interpret until you have manipulated it like the way we have done. And remember, improvement is in proportion to past production in DEA, but improvement is in proportion to potential improvement in MEA. Ladies and gentlemen, that brings us to the end of the entire caboodle